In the vast expanse of the universe, where galaxies stretch across unimaginable distances and time spans billions of years, one galaxy stands out as a true cosmic titan, IC 1101. Far larger than the Milky Way, and more massive than most galaxies ever discovered, this giant elliptical galaxy sits at the center of a massive galaxy cluster, quietly holding secrets about the formation and future of the universe. But how did it become so enormous? What lies at its core? And what can it tell us about the fate of all galaxies? In this video, we journey into the heart of IC 1101, the largest galaxy ever found, and uncover the astonishing truths behind its formation, its evolution, and its place in the grand story of the cosmos. Located over 1 billion light-years away from Earth in the constellation Virgo, IC 1101 resides at the heart of the Able 2029 galaxy cluster. And even though it lies far beyond the reach of our naked eyes, its sheer scale sends ripples of awe through the minds of astronomers and astrophysicists. To truly grasp what IC 1101 represents, we must first understand what galaxies are, how they form, and what makes IC 1101 so extraordinarily different from the rest. Galaxies are not merely groups of stars. They are gravitational ecosystems, interwoven webs of light and matter that form the very framework of the universe. There are small galaxies, like dwarf ellipticals, with just a few billion stars. And then, there are massive spiral galaxies like our own Milky Way, home to hundreds of billions of suns. Yet, IC 1101 doesn't just stand above the rest, it towers above them like a mountain towers above pebbles. At its core, IC 1101 is classified as a supergiant elliptical galaxy. Unlike the familiar swirling arms of a spiral galaxy, elliptical galaxies appear as elongated spheres or flattened footballs of light, lacking defined structure but rich in aged stars. And IC 1101 isn't just elliptical, it's the king of them all. While the Milky Way stretches about 100,000 light-years in diameter, IC 1101 has a diameter that may exceed 400,000 to 500,000 light-years, possibly even more, depending on how its outer halo is defined. Let that sink in. A galaxy so vast that light would take nearly 500,000 years to travel from one end to the other. And remember, light moves at nearly 300,000 kilometers per second. To put this in perspective, if you were to replace the Milky Way with IC 1101 in our position in space, it would consume not only our own galaxy, but also Andromeda, the Triangulum galaxy, and countless dwarf galaxies in the local group. We're talking about a single galaxy that could swallow an entire galactic neighborhood whole. The story of IC 1101 begins not with the stars, but with its location, Able 2029. Galaxy clusters like Able 2029 are among the most massive structures in the universe, consisting of thousands of galaxies bound together by gravity, submerged in vast clouds of superheated gas, and the invisible scaffolding of dark matter. These clusters are war zones of cosmic interaction. Galaxies collide, merge, and are stripped apart by gravitational tides. And in the heart of these clusters, massive galaxies like IC 1101 emerge, not through peaceful accumulation, but through a history of violent mergers and acquisitions. IC 1101 is what astronomers call a CD galaxy, or a central dominant galaxy. These titans are often found at the center of rich clusters, and they become what they are by consuming other galaxies. Over billions of years, smaller galaxies fall inward due to the gravitational pull of the cluster's core. They are pulled apart, their stars dispersed, and their stellar mass assimilated. This galactic cannibalism is one of the reasons IC 1101 is so huge. It has grown not just by forming stars, but by devouring other galaxies in its path, adding their mass to its own, creating an ever-expanding halo of stars. But IC 1101 doesn't just impress by size. Its luminosity is staggering. The galaxy shines with the light of hundreds of trillions of stars, possibly more. And while spiral galaxies like ours have regions of active star formation, IC 1101 is a place of ancient starlight. Most of its stars are old and yellow, meaning the galaxy has passed its peak period of star formation. The interstellar gas needed to birth new stars has largely been used up or blown away by the fierce winds of ancient supernovae, and the titanic energy outbursts from its central black hole. Speaking of black holes, let's address the sleeping monster at the heart of this galactic giant. Though we don't yet have a confirmed mass for the central black hole of IC 1101, based on the size and mass of the galaxy itself, estimates suggest it could be a supermassive black hole of tens of billions of solar masses, possibly approaching 100 billion times the mass of the Sun. That would make it one of the most massive black holes ever theorized. To call it a singularity is a disservice. It is a gravity well so deep and powerful that even light, the fastest thing in the universe, cannot escape it. Just imagine that for a moment. A black hole that dwarfs entire solar systems. A black hole so powerful that if it were placed where our Sun is, its event horizon, the boundary beyond which nothing can return, would stretch well past the orbit of Pluto, and possibly much further. And yet, for all its destructive power, it is silent, cold, and likely dormant, its feeding days perhaps long past. But how did IC 1101 become this massive? What mechanisms allowed it to accumulate such staggering size? Astronomers believe the key lies in hierarchical merging, a process where galaxies form and evolve through repeated collisions and mergers. In the early universe, small structures formed first. These primordial building blocks collided and fused, giving rise to larger and larger galaxies. Over billions of years, IC 1101, positioned perfectly in the gravitational center of a dense cluster, acted like a net, gathering galaxies that wandered too close. These mergers weren't gentle dances. They were violent affairs. Galaxies crashing into each other at speeds of hundreds or thousands of kilometers per second. Stars themselves rarely collide. Space is just too vast, but their orbits are thrown into chaos. Gas clouds are compressed, igniting bursts of star formation. Then the resulting supernovae explode, injecting energy into the surrounding space, and black holes merge to become ever larger. Each merger makes IC 1101 stronger, more massive, and more luminous. And yet, despite its might, IC 1101 is invisible to the naked eye. Even with powerful backyard telescopes, you wouldn't see more than a faint smudge. It takes advanced observational equipment, such as the Hubble Space Telescope, to truly detect and study this distant marvel. And what they've found paints a haunting picture. IC 1101 is ancient. Most of its stars are over 10 billion years old. That means this galaxy was already massive when the Earth was just forming. Before the first dinosaurs walked the planet. Before the Sun had even settled into its current stage of burning hydrogen, IC 1101 had already devoured countless galaxies. This makes IC 1101 not only large, but primordial, a relic from the deep time of the universe. In its golden glow, we see the echoes of a younger cosmos, a time when galaxies grew in a feeding frenzy, colliding and merging in the chaos of creation. But let us also ask, how do we know its size? How do we measure something so distant? Astronomers use various techniques, such as redshift measurements, luminosity profiling, and surface brightness distribution to estimate size and distance. IC 1101 has a redshift of about C equals 0.0777, corresponding to a light travel time of over 1 billion years. That means the light we see today left IC 1101 back when Earth's land masses were still shifting, and mammals were in their infancy. As the light from IC 1101 travels across the cosmic ocean, it stretches with the expansion of space itself, a phenomenon known as cosmological redshift. This is how we determine how far away it is, and by measuring the extent of its glow and applying our models of galactic structure, we estimate just how massive this titan truly is. And now, as we stare at the dim images of IC 1101 captured by telescopes, we're not just looking at a galaxy. We're looking at a monument. A monument built from the wreckage of countless smaller galaxies. A fossil from the ancient universe. A record of cosmic violence, growth, and evolution. Its core, the dense region that sits at the heart of IC 1101, holds an almost mythical status among astronomers. Unlike the modestly sized cores found in spiral galaxies like our Milky Way, IC 1101's core extends for tens of thousands of light-years. This core is not a gentle region where stars slowly meander through space. Rather, it's a seething, densely packed maelstrom of ancient stars, globular clusters, and almost certainly, a supermassive black hole that dwarfs any black hole found in our galactic neighborhood. This supermassive black hole, while not directly observed due to the limits of our current instruments, is inferred through the velocity dispersion of stars in the core. The gravitational forces needed to sustain such motion hint at a black hole possibly containing over 40 billion solar masses, or more. If confirmed, this would place IC 1101 among the hosts of the largest black holes ever theorized, if not the absolute largest. The existence of such a massive object also opens up countless questions. How could such a monstrous black hole form? Could it be the result of countless smaller black holes merging over eons? Or is it a unique object, born in an early universe governed by different physical laws? As we drift away from the core and venture toward the outer halo of IC 1101, we begin to enter a region where individual stars become sparse. Yet the size of this halo is one of the key defining features of IC 1101. It stretches over 1.04 million light-years in diameter, about 10 times larger than the Milky Way. It is in this staggering dimension that the true scale of IC 1101 becomes apparent. If placed at the center of our galaxy, it would stretch beyond the boundaries of our local group, potentially engulfing the Milky Way, the Andromeda Galaxy, and many of their satellite galaxies. The stars populating the outer regions are old and metal-poor, relics of ancient generations born before the universe had a chance to enrich its gas clouds with the heavy elements forged in stellar furnaces. This makes IC 1101 not only a massive galaxy but also an incredibly ancient one. Its outer regions contain stars that were formed more than 10 billion years ago, making it a kind of stellar graveyard, a fossil record of cosmic history dating back almost to the dawn of galaxy formation. Yet, for all its vastness, IC 1101 is curiously quiet. Unlike spiral galaxies with their elegant arms, active star formation, and bright nebulae, IC 1101 is a quiescent elliptical giant. It has long since used up most of its star-forming gas. The spectacular, luminous events that once filled its expanse with newborn stars and supernovae have quieted. What remains is a population of red, dying stars, slowly cooling as they burn through the last of their nuclear fuel. This quietness is deceptive. The formation of IC 1101 was anything but peaceful. Astronomers believe that it grew to its incredible size through countless galactic mergers, a process that may still be ongoing. Each collision stripped stars and gas from smaller galaxies, pulling them into IC 1101's gravitational grip. These events, called dry mergers when they lack gas, helped IC 1101 bulk up over billions of years. The remnants of these galactic meals are likely scattered throughout its halo, in the form of diffuse stellar streams and ancient star clusters, cosmic ghosts of galaxies that once were. Beyond the stars and gas, IC 1101 likely harbors a colossal amount of dark matter. Though invisible, dark matter reveals itself through gravitational lensing and the motion of stars. The galaxy's vast size and the speed at which its stars orbit suggest a dark matter halo that is truly staggering in scale, perhaps 100 trillion times the mass of our Sun. This dark matter forms the invisible skeleton upon which the luminous matter hangs, giving the galaxy its shape and anchoring it in the cosmic web of structure that binds the universe together. IC 1101 doesn't exist in isolation. It is the central galaxy of the able 2029 galaxy cluster, a massive collection of galaxies bound together by gravity. In many ways, IC 1101 is the gravitational anchor of this cluster, sitting at its heart like a monarch overseeing a vast kingdom of smaller galactic subjects. Its gravitational influence extends far beyond its visible halo, shaping the motions of galaxies throughout the cluster. The interactions within the cluster, including tidal forces, ram pressure stripping, and gravitational harassment, all feed into the ongoing evolution of IC 1101. Able 2029 itself is a wonder to behold. Spanning several million light-years and containing thousands of galaxies, it is one of the largest known galaxy clusters in the universe. The space between its galaxies is filled with superheated gas that glows in X-rays, a signature visible to space-based observatories like the Chandra X-ray Observatory. This gas, held in place by the cluster's gravity, provides a critical window into understanding the distribution of dark matter and the evolution of massive structures in the universe. IC 1101, as the dominant member of Able 2029, represents a pinnacle of galactic evolution. It is what happens when the gravitational dance of galaxies plays out for billions of years, allowing a single entity to consume its neighbors and grow fat on their remains. But this process is not limitless. Eventually, even the gravitational potential wells of such titanic galaxies reach a point of equilibrium, where further mergers become rare due to the expansion of the universe. Speaking of expansion, IC 1101's future is intimately tied to the fate of the cosmos itself. As the universe accelerates in its expansion due to dark energy, galaxies are drifting farther apart. This means that future civilizations, if any exist, within IC 1101 may find themselves increasingly isolated. The rich clusters of galaxies we observe today will eventually fade into darkness, leaving only the local groupings gravitationally bound. For IC 1101, that may mean a future where it slowly digests the last of its neighbors, and then drifts in a cosmic silence, cut off from the wider universe by the relentless expansion of space. But the story of IC 1101 is more than just its size. It is a living, breathing testament to the power of gravity, the evolution of matter, and the sculpting of structure across unimaginable timescales. It challenges our understanding of what galaxies are and how big they can grow. It forces us to re-examine the early universe, to question how such giants emerged so early in cosmic history. Was IC 1101 born differently? Did it have an early advantage, perhaps forming in a rare overdensity of dark matter and baryonic matter that allowed rapid early growth? Or is it simply the lucky survivor of countless mergers, each one a chance occurrence on the cosmic roulette wheel? The truth likely lies somewhere in between. What is certain is that IC 1101 represents a boundary in our understanding, a benchmark for what is possible in the universe. It dwarfs our Milky Way not only in size and mass but also in the ambition of its formation story. It is a galactic cathedral, a monument to time, gravity, and the strange beauty of the cosmos. As we continue to study IC 1101, each new observation reveals more about the underlying laws of the universe. It teaches us about galaxy formation, dark matter, supermassive black holes, and the fate of cosmic structures. It's not just a giant, it's a Rosetta Stone, encoded with secrets written in starlight and time. And as we peer deeper into the night sky, past the nebulae and star clusters of our own galaxy, beyond the gentle spirals and violent mergers of other galaxies, we find ourselves drawn to IC 1101 again and again. For in its quiet, ghostly glow lies a challenge. To understand it is to begin understanding the universe itself, not as it appears now, but as it has been for billions of years, and as it will be for billions more. To truly grasp the significance of IC 1101, one must step back and consider the fabric of the universe itself. Space, though seemingly empty, is structured into an immense cosmic web. This web is composed of dark matter filaments that connect clusters of galaxies across the universe, and IC 1101 sits as a central node within one of these massive intersections. These intersections, also known as nodes, are points of intense gravitational convergence, where galaxies are most likely to collide, merge, and grow. IC 1101, by virtue of its position in Able 2029, likely formed and grew at such a node, accumulating mass and structure from surrounding filaments over billions of years. What makes this particularly fascinating is that IC 1101 acts almost like a record keeper of this entire process. Each generation of stars within its core, each shell of dust and starlight layered across its halo, and each satellite galaxy now drawn into its orbit tells a story of a different cosmic era. These are not just stars but timelines, an observable archive of the cosmic epochs that preceded our own. As astronomers peer deeper into IC 1101 using spectroscopic analysis, they find not only the spectral fingerprints of different star types but also chemical evidence of how and when those stars formed. Heavier elements, like carbon, iron, and oxygen, formed in the cores of massive stars, and their presence in certain regions of IC 1101 indicates waves of past star formation and death. Some areas are richer in these elements, while others show signs of much older, more primitive stellar populations, which had little access to enriched interstellar material. These subtle chemical gradients speak to a complex evolutionary history, one shaped by waves of mergers, gravitational disruption, and episodic starburst events. And then there is the question of its color. Unlike the brilliant blue hues seen in actively star-forming galaxies, IC 1101 possesses a golden, almost amber-like glow, a color dominated by older, redder stars. This lack of blue light suggests that very little new star formation is occurring, indicating that the galaxy has transitioned into what astrophysicists refer to as a red and dead state. Yet even this dead state is a misnomer. While it may lack the fireworks of ongoing star birth, it remains a dynamic structure, shaped constantly by internal stellar dynamics, gravitational interactions, and the lingering effects of ancient collisions. Its lack of current star formation is also intriguing for what it implies about the galaxy's interstellar medium. For star formation to occur, galaxies must contain cold, dense molecular clouds, particularly clouds rich in hydrogen gas. IC 1101 appears to have exhausted, expelled, or heated the majority of its gas reservoir. This process may have been accelerated by feedback from its central supermassive black hole. When black holes accrete matter, they can emit vast amounts of energy in the form of radiation and relativistic jets, phenomena collectively referred to as active galactic nucleus, AGN, feedback. This feedback heats and disperses gas, suppressing the cooling mechanisms necessary for star formation. If IC 1101 once hosted a quasar, a highly luminous AGN, it may have ejected much of its cold gas long ago, effectively sterilizing itself from further growth through star formation. The supermassive black hole at IC 1101's core is, in many ways, the linchpin of this self-regulating system. Though hidden from direct view, it holds a gravitational grip over the central region. Its influence extends far beyond the accretion disk or the relativistic jets. It dictates the temperature and distribution of gas across a vast portion of the galaxy. In this way, IC 1101 illustrates one of the central principles of modern galactic evolution theory, that galaxies and their central black holes evolve in tandem, each influencing the fate of the other. But what happens when a galaxy becomes this massive? Is there a ceiling to galactic growth? In cosmological simulations, galaxies like IC 1101 appear as rare but not impossible occurrences. They form in regions of the universe where matter density is exceptionally high. However, these simulations also suggest that beyond a certain size, further growth becomes inefficient. As galaxies grow, their ability to pull in new material becomes counterbalanced by the expansion of space itself and by energetic feedback mechanisms like AGN-driven winds. IC 1101 may represent the natural limit, a cosmic maximum, of what gravity can assemble under the laws of our current universe. Even its satellite systems reveal interesting phenomena. Smaller galaxies orbiting IC 1101 are slowly being devoured through a process called galactic cannibalism. These interactions can take hundreds of millions of years. As a smaller galaxy approaches, tidal forces strip stars from its outer edges, leaving long, luminous trails, stellar streams, that arc across the halo of the host galaxy. These streams, some of which may still be visible in ultra-deep images of IC 1101, are evidence of past conquests, remnants of galactic entities that no longer exist independently. Moreover, the gravitational environment of IC 1101 warps the very space around it. Light from background galaxies is bent and distorted as it travels through the massive gravitational field created by IC 1101 and the Able 2029 cluster. This effect, known as gravitational lensing, has become a critical tool in modern astrophysics. By analyzing these distorted light paths, astronomers can map the invisible dark matter halo that envelopes the galaxy, one of the only ways to study dark matter directly. IC 1101, with its colossal mass and high gravitational lensing potential, is an ideal natural laboratory for this kind of research. Its X-ray emissions also tell an important tale. Space telescopes equipped to detect high-energy radiation reveal that IC 1101 is surrounded by a diffuse, hot atmosphere of plasma, reaching temperatures of millions of degrees Kelvin. This plasma, too hot to collapse into stars, is thought to result from the accumulated energy of many galactic mergers and the influence of the central black hole. The detection of iron and other heavy elements in this plasma further suggests that multiple generations of supernovae have enriched the intergalactic medium, seeding the environment with the building blocks of life, even if life as we know it never had a chance to develop in the sterile confines of IC 1101. Yet for all its mass, IC 1101 is just one galaxy among trillions. Its uniqueness lies not just in its sheer size but in the mysteries it presents. Could other IC 1101-like giants be hiding beyond the observational limits of our telescopes? Could there be even larger structures in the early universe, obscured by distance, dust, or cosmic redshift? These are not just idle questions, they are clues in the ongoing quest to understand how the cosmos formed, evolved, and continues to change. The study of IC 1101 also forces us to confront the impermanence of everything we see. Even this titan will one day fade. Its stars, though long-lived, will eventually exhaust their fuel. Over trillions of years, the last of its stellar populations will dim, and the galaxy will become a cold, dark shell, a fossil of the universe's most active epoch. Black holes will eventually evaporate through Hawking radiation, albeit over incomprehensibly long timescales. In the far future, IC 1101 may become an empty echo of its former grandeur, drifting in a dark, dying universe. But for now, in the present, IC 1101 remains a marvel. A beacon. A challenge. Its very existence pushes the boundaries of what we thought galaxies could be. It inspires awe not just because of its statistics, its diameter, its mass, its light, but because it represents the culmination of natural processes that began just moments after the Big Bang. It stands at the apex of complexity forged through time, gravity, and energy, a masterpiece sculpted from the raw materials of the universe itself. IC 1101's light travels across over 1 billion light-years just to reach our eyes, meaning what we see is a glimpse of an ancient moment in cosmic history. By the time this light washes across our planet, the galaxy may have already changed in subtle or profound ways. In this sense, we are looking into a museum of the distant past, preserved in starlight. Each photon captured by a telescope carries information about its origin point, the spectrum, the motion, the distance, all embedded in the subtle dance of electromagnetic waves. It is through decoding this silent light that we reconstruct the grandeur of IC 1101. When considering the galaxy's structure, astronomers have noted that it possesses an extraordinarily diffuse outer envelope. Unlike spiral galaxies with their tight, well-defined disks, IC 1101 seems to taper gently into the darkness of intergalactic space, with its brightness decreasing slowly over a vast radius. This extended light profile, commonly called a CD envelope, is a hallmark of galaxies that have undergone countless mergers. It's not simply large in a linear sense, but more like a gravitational sponge that has soaked in material from its surroundings across eons, its borders swelling with the accumulated remains of its neighbors. This diffuse envelope likely contains stars that were stripped from their host galaxies during high-speed flybys and gravitational interactions. These stars, no longer bound to a single galactic nucleus, instead orbit freely in the massive gravitational well of IC 1101. As a result, the halo becomes a glowing graveyard of stellar remnants, a hazy blend of starlight from sources long forgotten. These orphan stars carry with them ancient chemical signatures and orbital paths that speak to the violent history of galactic assembly. As we examine the core of the galaxy, we find the densest concentration of mass and light. The central region of IC 1101 glows with the combined luminescence of trillions of stars, packed into a relatively compact volume. Here, stellar densities are extreme. The gravitational forces are immense. It is within this region that the central supermassive black hole resides, likely one of the largest ever theorized, with mass estimates approaching 100 billion times that of our Sun. For context, the black hole at the center of the Milky Way, Sagittarius A, has a mass of about 4 million solar masses. The black hole at the heart of IC 1101 dwarfs it by several orders of magnitude. The existence of such a leviathan raises deep questions about the growth mechanisms of black holes. Did this giant grow steadily, feeding off gas and stars over eons, or did it rapidly balloon in mass through the merger of multiple massive black holes during galaxy collisions? If the latter, then the early universe must have contained unusually large seed black holes to begin with, perhaps formed directly from the collapse of massive gas clouds rather than the remnants of stars. These are the very questions that modern astrophysics seeks to answer through both observations and simulations. In analyzing the galactic dynamics, astronomers employ a range of tools, including redshift measurements to determine velocity dispersions across the galaxy. These measurements reveal how fast stars and gas clouds are moving within the galaxy, an indirect but powerful method to infer total mass, including the elusive dark matter. In IC 1101, the velocity dispersion is staggeringly high, indicating the presence of an enormous gravitational potential. This is how we know the visible matter, stars, gas, dust, accounts for only a fraction of the galaxy's true mass. The rest is dark matter, an invisible scaffold that holds the galaxy together. Dark matter, though never directly observed, manifests through its gravitational influence. It prevents galaxies like IC 1101 from flying apart under the centrifugal force of their own rotation. It also contributes to the stability of galaxy clusters like Able 2029. Without it, the galaxies would drift apart, unable to maintain the cluster's tight configuration. Dark matter is thus both a mystery and a necessity, a cosmic glue holding the large-scale structure of the universe in place. IC 1101's dark matter halo is likely one of the most massive ever inferred, stretching far beyond the luminous borders of the galaxy itself. The question of environment is also central to understanding IC 1101. Galaxies are not islands unto themselves but products of their neighborhoods. The Able 2029 cluster, in which IC 1101 resides, is a gravitationally bound collection of galaxies, hot gas, and dark matter. It is one of the most massive and richest clusters known, with a population of thousands of galaxies. IC 1101 occupies the central position, both figuratively and literally, the gravitational hub around which smaller galaxies orbit. Its privileged location at the cluster's center means it has had ample opportunity to cannibalize smaller galaxies drifting too close. These interactions are not gentle mergers but violent, transformative collisions. As galaxies plunge into the dense center of the cluster, they are subjected to intense gravitational forces, tidal stripping, and ram pressure interactions with the hot intracluster gas. Their own stars are ripped away. Their gas is heated and dispersed. Their morphologies are distorted beyond recognition. The end result is often their full assimilation into the central giant, IC 1101. From a cosmological perspective, IC 1101 is a success story of gravitational hierarchy. In the early universe, density fluctuations in the cosmic microwave background, tiny overdensities in an otherwise uniform sea of radiation, served as seeds for structure formation. Over billions of years, matter flowed into these regions, forming stars, galaxies, and clusters. Some areas, like that which formed Able 2029, accumulated more mass than others, allowing gravity to do more work, drawing in more material and growing ever larger. IC 1101 is the ultimate byproduct of this process, an apex predator in the cosmic ecosystem. It also serves as a powerful natural experiment for testing the limits of current astrophysical models. For example, simulations like Illustris and Millennium attempt to recreate large-scale structure formation from basic physical laws. These simulations have predicted the existence of massive CD galaxies like IC 1101, but each new observation helps refine those models, pushing the boundaries of what we think is possible in galaxy evolution. On Earth, the study of IC 1101 has captivated not only scientists but also science communicators and artists alike. Its sheer size and isolation provoke philosophical wonder. It challenges our sense of scale and our place in the universe. In educational media, it is frequently cited as the largest galaxy ever discovered, a beacon of cosmic extremity. There's a deeply human tendency to look skyward and seek out the biggest, the brightest, the most extreme. IC 1101 fulfills that role admirably. Yet beyond the awe it inspires, it also humbles. When we think of it, its 400,000 light-year diameter, its hundreds of trillions of stars, its supermassive black hole, we are reminded of how infinitesimally small we are. The entirety of human civilization could fit inside one of its stellar streams without ever being noticed. The solar system would be an invisible dot against its vast canvas. Even light itself struggles against its enormity. Traveling at 186,000 miles per second, it would still take over 400,000 years to cross from one side of IC 1101 to the other. And if you stood at one end, watching a supernova erupt on the opposite fringe, that light would not reach you until long after your civilization had risen and fallen. In this way, IC 1101 is not just a physical structure, it is a monument to deep time. And yet, despite its grandeur, it is not eternal. The cosmos changes. Stars burn out. Black holes evaporate. Clusters disperse. IC 1101 is an apex now, but entropy knows no favorites. Over incomprehensible timescales, its stars will grow cold and fade. Its black hole will grow silent. Its halo will thin. And in the heat death of the universe, even IC 1101 will surrender to darkness. Still, as of now, it stands. It rotates. It radiates. It exists as both relic and ruler, a reminder of what time and gravity can sculpt when given a billion years to work in silence. Its presence in the vast cosmic theater is not merely symbolic or abstract, it is the culmination of countless individual processes, each governed by the laws of physics, acting over incomprehensible stretches of time. The formation of its stars began when ancient clouds of hydrogen collapsed under gravity, igniting nuclear fusion in their cores. These stars lived out their lifespans, some for billions of years, others just millions. Some exploded in brilliant supernovae, scattering heavy elements across their galactic neighborhoods. These remnants became the raw material for new stars, new planetary systems, and potentially, if conditions ever permitted, the ingredients for life itself, though in such a hostile and turbulent environment as IC 1101, life as we understand it may never have found footing. The chemical evolution of IC 1101 is also a subject of deep interest. When we look at the spectrum of light it emits, we can decode the chemical fingerprints of its stars. These fingerprints tell us the story of nucleosynthesis, the gradual buildup of heavier elements from hydrogen and helium. The presence of elements like carbon, oxygen, iron, and magnesium within the galaxy's stars is not merely academic. These are the same elements found in our own bodies. The calcium in our bones, the iron in our blood, the oxygen we breathe. These elements were forged in the cores of stars like those in IC 1101, and in their explosive deaths. The galactic winds within IC 1101, vast currents of hot gas blown outward by supernovae, and the active galactic nucleus, help to distribute these elements across enormous distances. These winds shape star formation, influence galactic structure, and regulate growth. In more massive galaxies like IC 1101, the gravitational pull is so strong that much of this material is eventually pulled back in, leading to cyclical processes of enrichment and starburst activity. In this way, IC 1101 has likely undergone many seasons of creation and quiescence, periods where star formation surged and then slowed, only to flare up again as conditions permitted. Within this dynamic environment, the question of star formation efficiency becomes critical. Star formation is not a uniform process. It depends on gas density, temperature, metallicity, and turbulence. In some regions of IC 1101, stars may have formed prolifically, birthing massive, short-lived stars that burned brightly and died young. In other regions, star formation may have been stifled by feedback mechanisms or environmental pressures from the dense cluster environment. This uneven process results in a galaxy with a rich variety of stellar populations, from ancient red giants to newer blue main-sequence stars. Adding to this complexity are globular clusters, dense spheres of ancient stars that orbit the galaxy like satellites. These clusters, each containing hundreds of thousands of stars, are among the oldest known structures in the universe. In IC 1101, astronomers have identified an unusually high number of globular clusters, suggesting a tumultuous and active merger history. These clusters are not merely decorative. They serve as living fossils, preserving the chemical and dynamical history of the galaxy in their tightly bound cores. Studying their orbits, compositions, and ages provides critical insight into the processes that built IC 1101. But the full extent of IC 1101's complexity cannot be grasped without considering its interaction with the intergalactic medium. The space between galaxies in a cluster like Able 2029 is not empty. It is filled with a hot, X-ray emitting plasma composed of ionized gas. This intracluster medium plays a major role in galactic evolution. As galaxies move through this medium, they experience ram pressure, a kind of cosmic headwind that strips gas from their outer regions. This process, known as ram pressure stripping, is one of the primary mechanisms by which galaxies lose the fuel needed for star formation. IC 1101, being at the center of this maelstrom, is both the victim and the beneficiary of these effects, losing some material to the cluster, while gaining mass through mergers and accretion. This relationship is further complicated by the presence of gravitational lensing. The enormous mass of IC 1101 and its host cluster can bend the fabric of spacetime, distorting and magnifying the light of background galaxies. These cosmic lenses are not only beautiful, they are valuable tools for probing the distribution of dark matter and studying the early universe. In images captured by telescopes like Hubble and Chandra, the distortions around IC 1101 are clearly visible, arcs of light and smeared shapes betraying the presence of unseen mass. Through gravitational lensing, IC 1101 becomes a kind of cosmic telescope, allowing us to peer even deeper into the universe. The very light that it bends may have come from galaxies billions of years older than itself. In this way, IC 1101 is not just an object of study, it is also an instrument, a facilitator of discovery. Its role in the cosmos is multifaceted. It is both subject and lens, a product of ancient physics and a tool for understanding them. Meanwhile, the radiation emitted from its central black hole, a remnant of its more active quasar phase, continues to influence its surroundings. Though IC 1101 may no longer harbor a quasar, the traces of its past activity remain in the form of radio lobes, X-ray jets, and heated gas bubbles. These features hint at periods of intense energy release, when matter spiraled into the black hole and was converted into jets of relativistic particles. These outbursts help to heat the surrounding gas, inhibit star formation, and shape the galactic environment. In this way, the supermassive black hole did not merely sit at the center, it sculpted the galaxy from the inside out. In our pursuit to model these phenomena, scientists use powerful computational simulations, running on some of the fastest supercomputers in the world. These simulations track billions of particles, representing stars, gas, and dark matter, across cosmic time. They attempt to recreate structures like IC 1101 from the Big Bang to the present. By comparing these models with real observations, astronomers refine our understanding of galaxy formation, test the limits of gravitational physics, and explore alternative cosmologies. IC 1101 provides a real-world benchmark, a test case for the predictions made by these simulations. Looking to the future, one cannot help but wonder what fate awaits IC 1101. As the universe continues its accelerated expansion, driven by dark energy, galaxy clusters will eventually become isolated. The cosmic web that binds the universe together today will stretch and fragment, leaving gravitationally bound clusters like Able 2029 as islands in an ever-darkening sea. Within this island, IC 1101 will persist as a central anchor, slowly consuming what remains of its satellite galaxies. Over the course of trillions of years, it may become even larger, more diffuse, and more quiescent. Star formation will grind to a halt. The galaxy will fade into infrared obscurity, and only the most stable, long-lived stars, red dwarfs, will remain to shine faintly. Even black holes, once thought eternal, are now understood to slowly evaporate through Hawking radiation. Over unimaginable timescales, the supermassive black hole at IC 1101 center will shrink, emitting faint, nearly undetectable radiation until it vanishes altogether. The galaxy that once defied scale and awed observers across the universe will end not with a bang, but with a whisper, its light extinguished, its mass dispersed, its memory preserved only in the echoes of photons captured by distant, ancient civilizations or machines. Yet for now, IC 1101 remains a colossus, a structure of impossible grandeur, a witness to the full arc of galactic history, and a sentinel for the mysteries that still elude our grasp. The legacy of IC 1101 stretches beyond the visible, beyond even the measurable. As we dive deeper into its structure, its presence challenges the philosophical boundaries of our understanding. It is not merely a physical construct, it is a statement by the universe about scale, time, and endurance. The sheer number of stars within it, hundreds of trillions, is staggering. Each of those stars may have planets. Each of those planets may have moons. Each of those moons could harbor unique geological stories, atmospheric compositions, or potential for conditions once capable of supporting life. IC 1101 is not a single object, it is a cosmos within a cosmos. The very light from IC 1101 carries secrets. Photons emitted millions or even billions of years ago have only now reached our telescopes. When we look at IC 1101, we are not seeing it as it is, but as it was. It is a time machine, allowing us to study the cosmic past. The core of the galaxy may have changed in those intervening years. New mergers may have occurred. Stars may have been born and died. Its black hole may have erupted in fresh jets of relativistic particles. Yet we are left only with the image of a prior epoch. The galaxy is teaching us patience and humility. It is teaching us the art of inference, of reconstructing a moving, changing object from a snapshot frozen in time. Consider the atmosphere of awe it inspires. This awe is not rooted solely in its dimensions or age, but in the implications it has for the cosmos at large. If IC 1101 exists, then how many others like it are out there, still undiscovered? The observable universe contains over 2 trillion galaxies, and yet IC 1101 stands out. It forces us to revisit the assumptions we make about typical galactic structure. It forces us to reevaluate our understanding of galactic limits and formation pathways. Its very existence widens the goalposts of what's possible in galactic evolution. Its light reaches us in every wavelength, from radio, where we see the long tendrils of past jet activity, to X-rays, which reveal the hot gas that permeates its core, to visible light, showing us the golden glow of its ancient stars. Each wavelength is a layer, a puzzle piece, an insight. We construct the picture bit by bit, like archaeologists gently uncovering a buried civilization. Its shape, spherical, elongated, and faintly structured, tells the story of gravitational shaping and violent past interactions. Elliptical galaxies are generally poor in structure, and IC 1101 is no exception, but within its smoothness lies a hidden chaos. This smooth outer appearance hides the remnant shells, ripples, and substructures of hundreds of swallowed galaxies. Even the gravitational forces at play within IC 1101 are immense. The gravitational binding energy required to hold such a structure together is mind-boggling. The escape velocity at various points in the galaxy would dwarf anything our solar system experiences. To launch a spacecraft from one end to another would require thousands of times more energy than what would be required within the Milky Way. These forces compress the interstellar medium, affecting gas distribution, cooling times, and star formation cycles. In such a titanic arena, even gravity behaves on a more intimidating scale. And what of its location? Sitting at the center of Able 2029, IC 1101 commands its environment. It is not merely present, it is central, dominant, gravitationally sovereign. All galaxies in the cluster feel its presence. Their paths are bent by its mass. The galaxy is both monarch and monument. It serves as an anchor, binding the cluster together like a keystone in a cosmic arch. The cluster's hot X-ray gas swirls in response to its gravity, and the entire dynamic equilibrium of Able 2029 depends on the weight and stability of IC 1101. We must not forget the potential for unseen satellites and companion galaxies. While many have already merged into the central mass of IC 1101, some may still orbit it, poised for future consumption. These smaller galaxies, pulled ever closer by tidal forces, experience galactic harassment, disruption of their structure, stripping of their gas, and eventual assimilation. Their orbits decay over time, drawn inexorably inward by dynamical friction, another key process in galaxy evolution. IC 1101 grows not by peaceful coexistence but by conquest, devouring the smaller to increase its own size and complexity. But even this growth has limits. Eventually, the supply of available galaxies within its reach will dwindle. The cosmic environment will change. The galaxy will no longer feed, but reflect. It will become a graveyard of stars, a silent structure in a darkening universe. As dark energy continues to accelerate the expansion of the cosmos, IC 1101 will become increasingly isolated. Distant galaxies will recede beyond the cosmic event horizon, leaving IC 1101 cut off from the larger universe. It will be alone, a remnant of a once crowded sky, a last testament to the universe's fertile past. Even so, for billions of years more, it will shine. Its stars, especially the smaller, more stable ones, will continue to burn. Red dwarfs, with lifespans measured in trillions of years, will illuminate the galactic edges. White dwarfs will cool slowly, becoming black dwarfs over unfathomable epochs. Neutron stars will spin endlessly, their pulses fading evermore. Black holes, stellar and supermassive, will wait in silence, slowly evaporating in the dim background of space. The story of IC 1101 is a story of endurance, not eternal, but staggeringly long in duration. It reminds us how brief our existence is by comparison. Yet IC 1101 also reminds us of our potential. Despite the gulf between us, we have seen it. Our species, bound to one planet, vulnerable to cosmic whims, has developed the eyes to perceive this distant colossus. We have built telescopes that pierce the veil of space and time. We have learned to interpret the messages encoded in light. In studying IC 1101, we are engaging in one of the most profound acts of cosmic communion. We are listening to a story billions of years in the making. We are participating in the universe's way of knowing itself. And that is perhaps the most humbling truth of all. IC 1101 may be distant, but its light has touched us. Its photons have entered our instruments, been analyzed by our algorithms, and understood by our minds. We carry a piece of it now, in our knowledge, in our wonder. It exists not only in space, but in our awareness. It has taken root in human consciousness. Long after our time has passed, long after our civilization has transformed or vanished, the story of IC 1101 may endure, recorded in digital archives, etched into the data of deep space observatories, whispered across the void by interstellar probes. So when we gaze upward, past the clouds, beyond the stars we can see, into the vast and silent dark, we remember that somewhere out there, beyond hundreds of millions of light years, there lies a giant. A galaxy so large it defies our expectations, so ancient it witnessed the universe's youth, so powerful it has shaped everything around it. IC 1101 is not just a galaxy. It is a monument to the cosmos itself. Its mass, stretching into the range of over 100 trillion solar masses, defies comprehension. IC 1101 is not simply big, it redefines what we even consider possible in the structure of a galaxy. When we speak of galactic mass, we must account not only for the stars and visible matter but also for dark matter. Dark matter, still mysterious and undetectable directly, constitutes the bulk of IC 1101's mass. It acts as a cosmic glue, binding stars and gas into a coherent, gravitationally stable structure. Without it, the galaxy would tear itself apart from its own rotation and the turbulent histories of its mergers. It is this dark matter halo, invisible yet vast, that forms the unseen skeleton of IC 1101. The halo of IC 1101 could extend over several million light-years, far beyond its already massive visible disk. And it is within this halo that many of the cluster's smaller galaxies were once snared. One by one, over billions of years, these galaxies were pulled inward, stripped of their stars and gas, and added to the growing bulk of the central colossus. The stars of these consumed galaxies now drift throughout IC 1101's diffuse outer regions, remnants of long-forgotten systems. They are orphan stars, wandering far from their birthplaces, carried into the orbit of a gravitational monster that has no memory of its many meals. And the central core, how can we not return to it? The very nucleus of IC 1101 is likely home to a supermassive black hole of unimaginable size, estimated to weigh in at tens of billions of solar masses. If confirmed, it would be one of the most massive black holes ever discovered, a fitting crown for the largest galaxy known. This black hole would have once shone with the brilliance of a quasar, its accretion disk radiating as matter spiraled in at nearly the speed of light. These early periods of intense energy output shaped the surrounding galaxy, blowing out gas, halting star formation, and creating vast cavities in the surrounding intergalactic medium. What now appears calm and quiet was once the site of galactic-scale violence. Such feedback mechanisms are critical to the evolution of massive galaxies like IC 1101. The interplay between the central black hole and the galaxy's gas supply determines how fast stars can form, how dense the central regions can become, and even how much radiation escapes into the surrounding cluster. Powerful jets, launched from near the event horizon of the black hole, can extend for hundreds of thousands of light-years, carving through space like cosmic lances. These jets heat the surrounding gas, preventing it from cooling and collapsing into new stars. Thus, IC 1101 is a graveyard not just because its stars are old, but because its black hole has actively prevented the birth of new generations. Even its color tells a story. IC 1101 is a pale, golden yellow, a hue that speaks of stellar populations that are old and metal-rich. Blue, massive stars are short-lived, and their absence means star formation has long since ended. What we see now are long-lived red and yellow stars, steady in their glow, marking the galaxy's ancient heritage. Each of those stars has burned for billions of years, and many more will continue for trillions more. But they are a fading chorus in a song that is winding down. The galaxy is entering its twilight, not in terms of size, but in vitality. Now consider the structure of IC 1101 from a gravitational perspective. If you could stand on a hypothetical planet orbiting one of its stars, unlikely as that may be, and look up at its night sky, the scene would be dramatically different from Earth's. The sky would be filled with the glow of billions of nearby stars, many of them much closer than we are accustomed to. The night would never truly be dark. The central bulge of the galaxy would stretch across the heavens, a golden river of starlight. The density of stars, especially near the core, would make space travel an entirely different challenge, filled with hazards and opportunities alike. Yet for all this grandeur, IC 1101 remains elusive. Its distance, over 1 billion light-years, makes direct observation a challenge. It is not something you can see with a backyard telescope. Even many large observatories must peer carefully to resolve its light against the dense background of the universe. And that light, faint and stretched by redshift, is a whisper from a different time. It tells us what the galaxy was, not what it is. In this way, IC 1101 is a fossil. It is a preserved relic of an older universe, and we study it not only to understand its nature but to glimpse what the cosmos looked like in a younger, more crowded era. Every detail we extract, its size, mass, brightness, distance, comes from painstaking analysis. Redshift measurements help us determine how far it is. Spectroscopy reveals the composition of its stars. Surface brightness profiles allow astronomers to trace how light falls off with distance from the center, helping to map the full extent of its diffuse halo. Computer simulations are then employed to reconstruct its history. By comparing IC 1101 to simulated galaxies, scientists can infer how many mergers it must have undergone, how fast it rotated in the past, and how its structure evolved over billions of years. And the story those simulations tell is awe-inspiring. IC 1101 likely began as a small proto-galaxy in the early universe, perhaps just a few 100 million years after the Big Bang. It merged with its neighbors repeatedly, growing larger with each collision. Eventually, it formed the heart of a growing cluster, Able 2029. As that cluster matured, gravity drew more galaxies inward, and IC 1101 continued to feed. Each new merger added stars, gas, and momentum. Each altered its structure slightly. Over cosmic time, it grew not just in size, but in dominance. It is likely that IC 1101 is still growing, albeit slowly. The cluster itself may still contain galaxies on decaying orbits, spiraling ever inward. And as it consumes more, its outer halo expands further, growing even fainter and more diffuse. There may be stars in its outer regions so distant from the core that they take 1 billion years to complete a single orbit. For those stars, the galaxy is not a central body, it is a gravitational background, shaping their paths from an unfathomable distance. Such stars, barely bound to the galaxy, drift in the outskirts of its vast halo like cosmic castaways. Their existence blurs the boundaries between what is part of the galaxy and what is intergalactic space. These distant, wandering stars may represent the final vestiges of galaxies torn apart eons ago, stellar remnants that survived the chaos of merger events, now tracing slow arcs around a galactic core they will never approach within their lifetimes. Their motions are dictated not only by the visible mass of IC 1101 but by its titanic dark matter halo, extending far beyond what we can see or measure directly. Dark matter, in fact, may hold the key to understanding how IC 1101 achieved its size. Observations suggest that galaxies can only grow to such extreme proportions when they reside at the center of an extraordinarily massive dark matter concentration. This hidden framework not only attracts more matter but also protects the central galaxy from the destabilizing effects of rapid infall. IC 1101's immense gravitational well would have acted like a magnet for nearby galaxies and gas streams, drawing them in and accelerating their collapse into the growing behemoth. Without this unseen architecture, the galaxy we observe today could not exist. Moreover, the environment around IC 1101 has influenced its growth and structure in critical ways. Residing in the heart of Able 2029, a galaxy cluster of remarkable size and density, IC 1101 is immersed in a sea of hot, X-ray emitting gas. This intracluster medium, heated to millions of degrees, glows with high-energy photons and acts as both a record and regulator of galactic evolution. It's a hostile environment for star formation, as any cold gas clouds are rapidly stripped, heated, or dispersed before they can collapse into new stars. This explains the galaxy's old, reddish hue and its lack of new stellar nurseries. But even in this vast, superheated void, IC 1101 exerts influence. Its mass bends light from more distant galaxies behind it, creating gravitational lensing effects that allow astronomers to map the distribution of dark matter around it. The arcs and distortions we observe in the background sky reveal the contours of this hidden skeleton. In this way, IC 1101 does more than exist. It serves as a natural observatory for the deeper, more mysterious mechanics of the universe itself. And then there's the question of entropy, of heat death, of cosmic timelines so vast they render even billions of years insignificant. IC 1101, like all galaxies, is subject to the laws of thermodynamics. Over time, its stars will burn out. No new ones will replace them. Its central black hole will continue to grow by consuming gas, stars, and possibly even other black holes, but eventually even that will end. In the unimaginably distant future, when the universe is dark, quiet, and expanding beyond the reach of light itself, IC 1101 may remain as one of the final beacons, faint, enormous, and ancient beyond measure. To reflect on IC 1101 is to contemplate the upper limits of scale in a universe already dominated by vastness. Where most galaxies are islands of a few 100 billion stars, IC 1101 is a continent. It is not a simple extension of the norm, but a structure so vast and complex that it challenges our very definitions. It prompts us to reconsider what is possible within the framework of cosmic evolution. It asks, what happens when the process of galactic merging is allowed to continue uninterrupted for the age of the universe? IC 1101 is the answer. And yet, it might not be alone in its category. It is possible that, in the depths of the observable universe, and beyond it, there are other galaxies of similar or even greater size. We may not see them due to distance, redshift, or cosmic dust. They may lie in clusters we have yet to survey, hidden behind other structures or just beyond the edge of our instrument's sensitivity. IC 1101 is the largest we have found, but not necessarily the largest that exists. There is something both humbling and exhilarating in that thought. The cosmos is not static, and neither is our understanding of it. New instruments, like the James Webb Space Telescope, massive ground-based observatories, and next-generation survey missions, will continue to push the frontier of discovery. They may reveal more galaxies like IC 1101, or even suggest that our current models underestimate the true diversity of galactic giants. In studying IC 1101, we are not merely cataloging a curiosity. We are probing the limits of cosmic structure formation, testing the bounds of dark matter influence, and refining our understanding of how galaxies come to be. We are asking fundamental questions about scale, age, and process. Every observation, every data point adds another thread to the tapestry of cosmic history, a tapestry woven over billions of years and stretching across the observable universe. This galaxy, so far removed in time and space, teaches us not just about astronomy, but about humility. It reminds us of our place in the cosmos, not central, not special, but part of a universe rich with grandeur beyond anything we can easily comprehend. It suggests that there is still much to learn, to explore, to marvel at. It tells us that the universe is old, vast, and still full of secrets. And while IC 1101 may seem like a static monument to cosmic history, it remains dynamic in the sense that it continues to affect its surroundings. It continues to bend light, to distort spacetime, to influence the motion of its neighboring galaxies. Its central black hole may still emit flares of radiation, detectable from afar. It may still be accreting material, albeit slowly, from its immediate environment. It may continue to grow, inch by inch, toward a size we cannot yet conceive. Even its quietude is a form of activity. A galaxy doesn't have to blaze with star formation to be powerful. IC 1101 is the product of epochs of violence, now stilled. Its silence is the echo of countless cataclysms, frozen in time and space. To peer into it is to look into the eyes of the universe itself, to see not a single object, but a summation of cosmic evolution, of gravity at work, of time unspooling in the dark. As we continue to examine IC 1101, we are drawn into the intricacies of its formation and its future. The galaxy's current state, with its old stars and absent stellar nurseries, represents the culmination of a long and tumultuous history. The last stages of star formation within it were likely halted by the strong gravitational influence of the supermassive black hole at its center. The energetic output from the black hole, through processes like its accretion disk and powerful jets, created a feedback loop that prevented gas from cooling and collapsing into new stars. This halting of star formation is a key characteristic of many massive elliptical galaxies, which, like IC 1101, are often considered red and dead, meaning they no longer experience active star formation and instead consist of aging stars. But while IC 1101's current stage may seem like a peaceful, even dormant period, its future will unfold over unimaginable timescales. Galaxies like IC 1101, with their massive central black holes, tend to experience a slow, inexorable process of black hole growth as they continue to accrete matter from the surrounding space. The black hole at the center of IC 1101, which could be tens of billions of solar masses in size, will likely continue to grow, consuming nearby gas and stars, and possibly even other smaller black holes. However, as it consumes more material, it may gradually run out of fuel. When this happens, the quasar-like activity that once powered the galaxy will subside, and IC 1101 will enter an era of true dormancy. It will become a quiet, passive giant, slowly losing energy as it fades into the distant future. The timeline for this phase, though, stretches far beyond human comprehension. The cosmic timescale in which IC 1101 exists means that it will continue to shine with its aging stars for hundreds of billions of years. Even though star formation has long since ceased, the existing stars will continue to burn, and new generations of stars will never form. The dark matter halo, the galaxy's unseen structure, will remain in place, helping to stabilize the galaxy's gravitational structure. One of the most fascinating aspects of IC 1101 is its role within its larger cosmic environment. The galaxy is not isolated, it is part of the Able 2029 galaxy cluster, a gravitationally bound system containing many other galaxies. This cluster, which spans roughly 2 million light-years across, is a massive cosmic structure that represents one of the most dense regions in the universe. The presence of IC 1101 at the center of Able 2029 highlights the importance of galaxy clusters in the formation and evolution of massive galaxies. IC 1101's position within this cluster is not by chance. It has grown to its massive size by merging with smaller galaxies, gradually accreting stars, gas, and dark matter over billions of years. This cluster, like other galaxy clusters, is a hub of galactic interactions. In such environments, galaxies are constantly being pulled and tugged by the gravitational forces of their neighbors. This dynamic environment promotes the merging and stripping of galaxies, events that have long-lasting effects on the galaxies involved. For IC 1101, the mergers it has experienced with other galaxies in the cluster have been pivotal in shaping its current form. As these smaller galaxies fell into the gravitational well of IC 1101, they were stretched and torn apart, with their stars being absorbed into the larger galaxy's stellar population. Over time, the process of accretion and cannibalism has contributed significantly to IC 1101's extraordinary size and mass. Looking at IC 1101, we are not just observing a single galaxy but a monumental process of cosmic evolution. Galaxies are not static objects, they are dynamic entities that change, grow, and evolve over time. IC 1101 is a prime example of this, representing a late stage in the life cycle of galaxies that are born from smaller seeds and gradually grow through mergers and accretion. In a sense, IC 1101 is the culmination of the universe's ongoing process of galactic assembly, a final testament to the strength of gravitational forces that shape everything in the cosmos. The future of IC 1101, like all galaxies, is inexorably linked to the expansion of the universe. As the universe continues to stretch and galaxies move further apart, the dynamics of galaxy clusters like Able 2029 will change. The gravitational interactions that have led to IC 1101's massive size will slowly diminish as galaxies drift farther away from each other. Eventually, the cosmic expansion will become the dominant force, and the interactions between galaxies will become much less frequent. This process, which will unfold over billions of years, will see the universe becoming more isolated, with galaxies scattered in vast, empty regions of space. But before this happens, IC 1101 will continue to serve as an example of the power of gravity, the resilience of galactic structures, and the endless cycles of cosmic rebirth. It will remain one of the largest and most massive galaxies in the universe, a cosmic behemoth that continues to influence its surroundings. Whether it is through the cosmic remnants of galaxies it has devoured or the powerful gravitational lensing effects it produces, IC 1101 will continue to shape the universe around it for an incomprehensibly long time. In the end, IC 1101 is a reminder of the vastness of space, the unimaginable scale of the universe, and the intricate dance of galaxies that have shaped the cosmos for billions of years. It is not simply a large galaxy. It is a testament to the forces that govern the universe. Every star, every planet, and every black hole within IC 1101 carries the echoes of ancient cosmic events, mergers, accretions, and the slow but unstoppable march of time. What IC 1101 teaches us is not just about the size and scale of galaxies, but about the processes that drive cosmic evolution. From its formation at the heart of a galaxy cluster to its current state as a passive giant, IC 1101 has been shaped by the forces of gravity, dark matter, and cosmic interactions. Its story is not unique, but it is one of the most extreme examples of what can happen when galaxies collide and grow over vast timescales. Ultimately, IC 1101 challenges our understanding of the universe. It forces us to reconsider what we thought we knew about galaxy formation, dark matter, and the limits of cosmic structures. It reminds us that, despite our best efforts, there is always more to discover in the universe. And as our tools and technologies continue to advance, we may one day uncover new secrets about IC 1101, and perhaps even discover new galaxies that are even more colossal, more ancient, and more mind-boggling than we can yet imagine. IC 1101 is not just a point on a map of the cosmos, it is a story. A story of the universe's most extreme gravitational forces, of galaxies merging, of stars dying and being reborn, and of the relentless passage of time that shapes the very fabric of existence. It stands as a reminder that in the vastness of space, there are still mysteries waiting to be uncovered, waiting to expand our understanding of the universe and our place within it. As we continue to explore the farthest reaches of space, IC 1101 will remain a beacon, a reminder of the sheer power and beauty of the cosmos, and a symbol of the infinite wonders that lie beyond our sight. IC 1101, a galaxy that has fascinated astronomers and laypeople alike, continues to offer an ever-expanding horizon for exploration and wonder. As we delve deeper into its remarkable features and its context in the broader universe, we begin to appreciate the galaxy not just as a scientific curiosity, but as a symbol of the complex forces that govern the cosmos. IC 1101's very existence raises questions about the fundamental nature of galaxies, how they evolve, and how the larger structure of the universe is organized. Let's consider the galaxy's role within the framework of galactic evolution. As one of the largest known galaxies, IC 1101 serves as an excellent example of the life cycle of galaxies in the universe. Galaxies are not permanent objects, they undergo profound changes over billions of years. Early in the universe's history, galaxies were small and formed from gas and dark matter that clumped together. Over time, these nascent galaxies collided, merged, and grew larger, often under the influence of gravity. IC 1101 is the product of this cosmic evolution, a galaxy that has undergone mergers with other galaxies in the able 2029 galaxy cluster and is the result of billions of years of galactic accretion. Understanding how IC 1101 came to be is a window into the life cycle of galaxies in general. One of the most captivating aspects of IC 1101 is its connection to the underlying dark matter structure of the universe. Dark matter, which makes up roughly 27% of the universe's mass energy content, is thought to play a crucial role in the formation of galaxies. It provides the gravitational framework that holds galaxies together and influences their growth. The dark matter halo surrounding IC 1101 is likely a significant factor in its immense size. The galaxy's growth has been greatly influenced by its interaction with the dark matter present in its environment, and this has made IC 1101 one of the most massive galaxies ever observed. In addition to dark matter, the study of IC 1101's supermassive black hole offers a further avenue for exploration. The black hole at the center of IC 1101 is estimated to be one of the largest known, perhaps as much as 40 billion solar masses. This black hole, like others in similar massive galaxies, likely plays a central role in regulating the growth of the galaxy itself. The feedback mechanisms triggered by the intense energy output of the black hole, particularly through the ejection of powerful jets of material, could have a profound effect on the surrounding environment. It's conceivable that the black hole has been responsible for shutting down star formation in the galaxy, limiting the growth of new stars by heating up the gas in the galaxy's core. This would explain why IC 1101 is predominantly made up of older stars and lacks the younger, blue stars commonly seen in more active galaxies. Moreover, the galaxy's quiescent state offers a valuable opportunity for scientists to study the final stages of galactic evolution. As galaxies like IC 1101 reach the end of their star-forming lives, they enter a phase where the remaining stars slowly burn through their fuel. This process plays out over hundreds of billions of years, far longer than human civilization could ever comprehend. The stars in IC 1101, having already consumed much of their hydrogen and helium, are now transitioning into red giants, or white dwarfs, marking the final stages of their stellar lives. The remnants of these stars will linger for eons, adding a sense of timelessness to the galaxy as a whole. While the galaxy is no longer creating new stars, it is far from dead. Instead, It is in a phase of slow decay, one that will persist for an incomprehensibly long time. Despite this dormancy, IC 1101's future is far from bleak. The gravitational forces that shape its structure are still at play. Galaxies like IC 1101 will continue to evolve, albeit at a much slower pace. Its supermassive black hole will eventually enter a phase where it no longer has the fuel to accrete material at high rates. This could lead to a gradual decrease in the energetic phenomena surrounding the black hole, transforming it from an active quasar into a more passive object. IC 1101 itself will continue to serve as a reminder of the extraordinary forces that govern the universe's largest objects. Even as the galaxy transitions into a quieter, more stable state, its gravitational influence will continue to shape the surrounding cluster. The larger Able 2029 galaxy cluster, of which IC 1101 is the centerpiece, provides further insights into the complex interactions that shape the evolution of galaxies. Galaxy clusters, by definition, are collections of hundreds to thousands of galaxies bound together by gravity. They are the largest gravitationally bound structures in the universe. Within these clusters, galaxies frequently interact through a variety of processes. The most dramatic of these is galaxy mergers, events where galaxies collide and combine to form even larger galaxies, like IC 1101. These mergers not only contribute to the growth of individual galaxies, but they also influence the cluster's overall structure. The presence of a galaxy as massive as IC 1101 at the center of Able 2029 demonstrates the importance of galaxy clusters in shaping the largest galaxies in the universe. IC 1101's central location within Able 2029 also raises intriguing questions about the future of the galaxy cluster itself. As the universe continues to expand, the galaxies within clusters will slowly move farther apart. The dynamics within these clusters will change, and eventually, the cluster will begin to dissolve. This process, known as the dying cluster, will result in the isolation of the galaxies within the cluster. For IC 1101, this could mean that it will eventually drift alone in the vastness of space, far from the other galaxies that once interacted with it. As the cluster begins to dissolve, IC 1101 may become increasingly isolated, left to slowly fade as the stars within it continue to burn out. Yet, even in this future, IC 1101 will remain a beacon of the incredible processes that have shaped galaxies over the course of cosmic history. It will stand as a testament to the power of gravity, the beauty of cosmic evolution, and the mysteries of the universe that continue to unfold. Every time scientists study IC 1101, they are uncovering new layers of understanding about the universe's largest structures, about the way galaxies grow, evolve, and ultimately reach the end of their star-forming lives. Even in its quiet, dormant state, IC 1101 is far from lifeless. The galaxy's stellar population continues to churn, albeit more slowly than in its earlier years. The aging stars within it provide a unique snapshot of the universe's past, offering insights into the processes that led to the formation of such massive objects. The study of galaxies like IC 1101 also holds clues about the formation of other galaxies, including the Milky Way. By understanding how massive galaxies form and evolve, we can gain a deeper understanding of the broader mechanisms that govern galactic life cycles. Through the continued study of IC 1101, we come to appreciate the immense scale of the universe, the intricate forces that govern it, and the incredible variety of objects that populate it. From the birth of stars to the death of galaxies, every aspect of cosmic evolution contributes to the grand narrative of the universe's unfolding story. IC 1101, as one of the largest galaxies ever discovered, stands as a profound example of the universe's capacity for creation and destruction, for growth and decay. It is a galaxy that speaks to the beauty and the mystery of the cosmos, inviting us to look deeper and ask more questions about the vast expanse of space. As we look to the future, we are reminded that the journey of understanding the universe is never truly over. Just as IC 1101 has evolved over billions of years, our understanding of it, and the cosmos as a whole, will continue to evolve as well. New discoveries, new technologies, and new methods of observation will unlock further mysteries hidden within galaxies like IC 1101. As we continue to push the boundaries of human knowledge, IC 1101 will remain a symbol of the extraordinary complexity and beauty of the universe. A universe that is still, in many ways, a vast and uncharted frontier. IC 1101's sheer magnitude and its position within the cosmic landscape invite us to reflect on the scale and complexity of the universe itself. It is a galaxy that reminds us just how much there is still to learn about the vastness of space, the intricacies of galactic formation, and the fundamental forces that govern the cosmos. The study of galaxies like IC 1101 serves as a humbling experience for scientists and enthusiasts alike, offering glimpses into a time and space far beyond our own. As the study of IC 1101 continues to unfold, we are also reminded of how far we've come in our understanding of the universe. A few centuries ago, our view of the cosmos was limited to the stars visible to the naked eye. It wasn't until the invention of the telescope that humanity began to peer deeper into the heavens, uncovering galaxies and objects that were previously unimaginable. Today, through the power of advanced telescopes like the Hubble Space Telescope, astronomers are able to study galaxies like IC 1101 in remarkable detail, providing us with insights into their structure, formation, and evolution. This leap in observational capabilities has dramatically changed our understanding of galaxies and their roles within the larger structure of the universe. Through the study of galaxies like IC 1101, we now know that galaxies come in all shapes and sizes, from the tiny dwarfs to the colossal ellipticals like IC 1101. We have discovered that galaxies can undergo dramatic transformations, growing through mergers and interactions with other galaxies, and that they can be shaped by the powerful influence of dark matter and supermassive black holes. But there's more to the story of IC 1101. As astronomers continue to study this behemoth of the cosmos, they have discovered that its size is not just a matter of scale. It also has profound implications for our understanding of the universe's formation and the forces that shaped it. IC 1101's immense size and its central role in the Able 2029 galaxy cluster point to a history of intense gravitational interactions and mergers. This process of galactic cannibalism, where smaller galaxies are absorbed into larger ones, is thought to have been a key driver in the growth of IC 1101. Over the course of billions of years, IC 1101 has likely merged with dozens, if not hundreds, of smaller galaxies, each contributing to its incredible size and mass. It is also important to note that galaxies like IC 1101 are not isolated islands in space. They are part of a much larger web of cosmic structures. The universe is made up of vast cosmic filaments, dense regions of matter that stretch across billions of light years, connecting galaxy clusters and superclusters. IC 1101's position in the Able 2029 galaxy cluster places it at the heart of one of these cosmic webs, surrounded by a large number of other galaxies. The gravitational interactions between these galaxies, as well as their movement within the cluster, play a significant role in shaping the properties of each individual galaxy. The study of IC 1101 also reveals important insights into the nature of galaxy clusters themselves. Galaxy clusters are not just random groupings of galaxies. They are dynamic and evolving systems. The galaxies within a cluster are constantly interacting with one another, through processes such as gravitational attraction, tidal forces, and the exchange of gas and stars. These interactions can have a profound impact on the galaxies themselves, leading to phenomena such as galaxy mergers, starbursts, and the creation of supermassive black holes. In the case of IC 1101, its position at the center of the Able 2029 cluster suggests that it has played a central role in the evolution of the cluster as a whole. The immense gravitational pull of IC 1101 has likely shaped the orbits and trajectories of the other galaxies in the cluster, and it may have played a key role in the overall structure and dynamics of the cluster. As IC 1101 continues to evolve, its interactions with the other galaxies in Able 2029 will undoubtedly continue to shape the future of the cluster. As we turn our attention to the broader implications of IC 1101's size and evolution, we are confronted with fundamental questions about the nature of the universe itself. Why do galaxies like IC 1101 exist? How did they come to be so massive? And what role do they play in the grand scheme of cosmic evolution? One possible answer lies in the role of dark matter. As mentioned earlier, dark matter is thought to play a critical role in the formation and growth of galaxies. Dark matter's gravitational influence is believed to be responsible for the formation of the first galaxies in the early universe, and it continues to shape the evolution of galaxies to this day. IC 1101's enormous size suggests that dark matter played a major role in its formation, and its dark matter halo may be a key factor in its continued growth. The study of IC 1101 provides a unique opportunity to investigate the relationship between dark matter and galactic formation, offering insights into how dark matter influences the structure of the universe on the largest scales. IC 1101's supermassive black hole also holds key clues to understanding the forces that govern the evolution of galaxies. Supermassive black holes are found at the centers of most large galaxies, and they play a crucial role in regulating the growth and behavior of the galaxy itself. The black hole at the center of IC 1101, with its estimated mass of 40 billion solar masses, is one of the largest known, and it likely exerts a powerful influence over the galaxy's evolution. The energy emitted by this black hole, in the form of radiation and powerful jets of material, could be responsible for suppressing star formation in the galaxy's core, effectively preventing the formation of new stars and contributing to the galaxy's aging population of stars. The study of IC 1101's black hole offers a rare opportunity to explore the role of supermassive black holes in the life cycles of galaxies and to gain insights into the processes that regulate the growth of the largest cosmic structures. As we continue to probe the depths of IC 1101 and other galaxies like it, we are reminded of the vastness and complexity of the universe. IC 1101, with its immense size and its role in the Able 2029 galaxy cluster, serves as a remarkable example of the power and mystery of the cosmos. It is a galaxy that has been shaped by the forces of gravity, dark matter, and supermassive black holes, and it continues to evolve and change as it moves through the cosmic landscape. The study of IC 1101 is far from complete, and as technology continues to advance, we will undoubtedly gain new insights into this extraordinary galaxy. The future of space exploration holds exciting possibilities, from new space telescopes that can observe distant galaxies in unprecedented detail to new theories and models that may shed light on the fundamental nature of the universe. As we continue to study IC 1101 and other galaxies like it, we move closer to answering some of the most profound questions about the universe and our place within it. But perhaps the most remarkable thing about IC 1101 is not just its size or its place in the cosmos, but the fact that it exists at all. In the grand scheme of the universe, galaxies like IC 1101 are but a brief moment in time. They are born, they evolve, and eventually, they will fade away. Yet, in that fleeting moment, they are a testament to the power of the universe's fundamental forces and the endless possibilities of cosmic evolution. The story of IC 1101 is, in many ways, the story of the universe itself, an ever-changing, ever-evolving process of creation, destruction, and rebirth. As we continue to gaze out into the vastness of space, we are reminded that there is so much more to discover, so much more to learn. And as we look at IC 1101, one of the largest galaxies ever discovered, we are reminded of the limitless potential of the universe and the infinite possibilities that lie ahead. IC 1101 stands as a testament to the complex and ever-changing nature of the universe. It is one of the few objects in the universe that can truly embody the idea of cosmic grandeur. Its existence pushes the boundaries of our understanding, not only of the mechanics of galaxies but also of the forces that drive their evolution over billions of years. As we continue to study IC 1101 and its role within the Able 2029 galaxy cluster, we come to realize that the secrets it holds could hold the keys to many fundamental questions about the formation and life cycle of galaxies. One of the most intriguing aspects of IC 1101 is its age. Unlike many of the younger, more active galaxies that populate the universe, IC 1101 is an ancient relic, formed billions of years ago, likely in the early stages of the universe. Its age and size make it an invaluable subject of study for astronomers trying to piece together the timeline of galactic evolution. The core of IC 1101, home to a massive concentration of stars, offers a glimpse into a stage of galactic evolution that is rarely seen in the present-day universe. Its stellar population is predominantly old, with relatively little star formation occurring in the galaxy's heart. This lack of new star formation in the center of IC 1101 is likely due to the massive black hole at its core. As we know from other galaxies, supermassive black holes have a profound influence on their host galaxies. The intense gravitational pull of these black holes can disrupt the gas and dust in the galaxy's center, preventing the material from collapsing into new stars. In the case of IC 1101, the black hole likely played a pivotal role in shutting down star formation in the galaxy's central regions, which is a common feature of massive elliptical galaxies. This is a fascinating aspect of the galaxy's evolution, as it highlights the delicate interplay between a galaxy's central black hole and the rate of star formation. Interestingly, the presence of such a massive black hole in IC 1101 has implications beyond just star formation. Supermassive black holes are believed to influence their surroundings through their energetic outflows. The black hole at the center of IC 1101 is capable of producing powerful jets of energy and matter that can extend far beyond the galaxy itself. These jets can have a profound effect on the surrounding intergalactic medium, potentially influencing the formation and evolution of nearby galaxies. The exact mechanics of these jets and their effects on galactic environments are still a subject of ongoing research. However, it is clear that IC 1101 supermassive black hole is not only shaping its own galaxy but may also be influencing the dynamics of its cosmic neighborhood. As we look outward from IC 1101 to the surrounding Able 2029 galaxy cluster, we can begin to appreciate the galaxy's role in the larger structure of the universe. Galaxy clusters are some of the most massive structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity. IC 1101's position at the center of the Able 2029 cluster places it in a pivotal role. It is not just one galaxy among many. It is the dominant member of the cluster, a gravitational anchor around which the other galaxies in the cluster revolve. The relationships between galaxies within clusters are incredibly complex, shaped by the forces of gravity, tidal interactions, and even the intracluster medium, the hot, diffuse gas that permeates the space between galaxies. Galaxy clusters like Able 2029 are essential laboratories for studying the larger-scale structure of the universe. They provide insights into how galaxies form, evolve, and interact with each other on cosmic timescales. The study of IC 1101, and its interaction with other galaxies in the Able 2029 cluster, has the potential to reveal key aspects of galaxy formation, the role of dark matter in galactic evolution, and the dynamics of the universe's largest structures. Beyond IC 1101 and the Able 2029 cluster, the study of supermassive galaxies provides insight into the processes that govern the early universe. Galaxies like IC 1101 are believed to have formed in the early stages of the universe's history, when cosmic conditions were much different from what we see today. They may hold clues to the processes that took place in the primordial universe, providing a window into the past that allows astronomers to better understand how the first galaxies emerged from the cosmic dark ages. The discovery of a galaxy like IC 1101 challenges our preconceived notions of galactic evolution, raising important questions about how massive structures like this could form and evolve over billions of years. One of the most fundamental questions that IC 1101 raises is the role of galaxy mergers in shaping the structure of the universe. Over the course of its life, IC 1101 has likely absorbed numerous smaller galaxies, growing larger and more massive with each merger. This process of galactic cannibalism is thought to be a major driver of the growth of the largest galaxies in the universe. As galaxies collide and merge, they transfer their stars, gas, and dark matter to the larger galaxy, resulting in an overall increase in mass and size. The role of galaxy mergers in the formation of supermassive galaxies like IC 1101 underscores the importance of gravitational interactions in shaping the cosmos. The immense size and mass of IC 1101 also provide insight into the mysterious force of dark matter. Dark matter, which makes up a significant portion of the mass of the universe, remains largely invisible to current observational methods. However, its gravitational influence can be detected in the way galaxies move and interact. In the case of IC 1101, its enormous size and mass are likely the result of the presence of dark matter, which provides the necessary gravitational pull to hold the galaxy together. By studying galaxies like IC 1101, astronomers are beginning to unravel the mystery of dark matter, gaining a deeper understanding of its role in the formation and evolution of cosmic structures. In addition to dark matter, the role of dark energy is also crucial in understanding the large-scale structure of the universe. Dark energy is a mysterious force that is driving the accelerated expansion of the universe. While the exact nature of dark energy remains elusive, its effects can be seen in the way galaxies and clusters of galaxies are moving apart. The study of galaxies like IC 1101 offers a unique opportunity to explore the interplay between dark matter, dark energy, and the evolution of cosmic structures. Understanding how these forces shape the universe on the largest scales is one of the key goals of modern cosmology. The sheer scale of IC 1101 also invites reflection on the future of the universe. While we are still in the early stages of studying galaxies like IC 1101, we are beginning to piece together a picture of the universe's long-term evolution. IC 1101 is an ancient galaxy, and its future is tied to the ongoing dynamics of the Abell 2029 galaxy cluster. As galaxies continue to interact and merge over billions of years, the structure of the universe will continue to evolve. Some predictions suggest that, in the far future, the universe will be dominated by large-scale structures like superclusters and massive elliptical galaxies. IC 1101 may one day be just one of many massive galaxies that dominate the cosmic landscape. For now, though, IC 1101 stands as a reminder of the mysteries of the universe. Its size, its position in the Abell 2029 cluster, and its complex history provide a window into the forces that shape the cosmos. The study of IC 1101 is not just about understanding a single galaxy. It is about understanding the fundamental processes that govern the formation and evolution of galaxies, and by extension, the universe itself. As we continue to explore the depths of space and uncover the secrets of galaxies like IC 1101, we are reminded of the limitless potential of human curiosity and the uncharted territory that lies ahead in our quest to understand the cosmos. The staggering size of IC 1101, estimated to span over 400,000 light-years, defies the common perception of what a galaxy should look like. To put this in perspective, our Milky Way galaxy spans approximately 100,000 light-years in diameter, meaning IC 1101 is over 4 times as large. This scale is almost incomprehensible. If you could travel at the speed of light, it would still take you hundreds of thousands of years just to cross from one end of IC 1101 to the other. This colossal size isn't just an anomaly, it's a hint at the remarkable processes that led to its formation, as well as the fundamental rules of the universe that allow such massive structures to exist and persist. The population of stars within IC 1101 is another element that contributes to its extraordinary nature. Estimates suggest it contains upwards of 100 trillion stars, which dwarfs the Milky Way's estimated 100 to 400 billion stars. This immense number of stars contributes to the galaxy's luminosity, making it a radiant beacon at the heart of the Abell 2029 cluster. However, the types of stars that inhabit IC 1101 differ from those in younger galaxies. The majority are older, yellow and red stars, aging celestial bodies that have long since exhausted the hydrogen fuel necessary for new star formation. This gives IC 1101 its signature golden hue, which is often observed in large elliptical galaxies. But where did all these stars come from? The most widely accepted theory is that IC 1101 grew through a series of galactic mergers. In the chaotic early universe, galaxies frequently collided and merged with one another. Each merger added mass to the growing galaxy, bringing in new stars, new gas, and most importantly, dark matter. These cosmic collisions didn't just add material, they also reshaped the structure of the resulting galaxy. Over time, as IC 1101 absorbed more and more galaxies, it transitioned from a spiral, or irregular shape to a massive elliptical form. This process of hierarchical merging is a cornerstone of modern galaxy formation theory, and IC 1101 serves as one of the most extreme examples of it. The interstellar medium of IC 1101, the gas and dust that exists between its stars, is also of interest. In younger, more active galaxies, this medium is often dense and turbulent, leading to frequent star formation. In contrast, IC 1101's interstellar medium is relatively depleted. This suggests that the galaxy has undergone a process known as quenching, where active star formation slows down or ceases entirely. This can occur due to a number of reasons. The gas needed for star formation may have been used up, expelled through galactic winds, or heated by interactions with the galaxy's supermassive black hole. In the case of IC 1101, it's likely a combination of these factors. As the galaxy aged and absorbed more material, the conditions for star formation became less favorable. Further magnifying the intrigue of IC 1101 is its central black hole. Supermassive black holes are believed to exist at the heart of nearly all large galaxies, and IC 1101 is no exception. In fact, given the galaxy's size, the black hole at its center is expected to be one of the most massive in the known universe. While it's difficult to measure the precise mass of this black hole due to its extreme distance, over 1 billion light-years from Earth, models predict that it could weigh in at tens of billions of times the mass of our Sun. Such a massive black hole would exert a powerful influence over its surroundings, generating intense gravitational forces and possibly emitting energetic jets and radiation from the accretion of matter. These outflows, driven by the black hole's intense energy, play a critical role in the galaxy's evolution. By heating the surrounding gas and expelling it into intergalactic space, these processes can prevent new stars from forming, effectively halting the growth of the galaxy in terms of stellar population. This feedback loop between the black hole and its host galaxy is a crucial component of modern galaxy evolution theories and helps explain why the largest galaxies tend to have little new star formation. Another component worth discussing is the presence of globular clusters within IC 1101. Globular clusters are spherical collections of stars that orbit the core of a galaxy. These clusters are among the oldest objects in the universe and often serve as historical records of a galaxy's early formation phases. Given the size and age of IC 1101, it likely contains hundreds of thousands of these clusters. The study of these ancient stellar groups can provide insights into the early stages of star formation and the chemical composition of the universe shortly after the Big Bang. Moreover, the galaxy is likely surrounded by an extensive halo of dark matter. Dark matter doesn't emit or absorb light, making it invisible to our telescopes, but its gravitational effects can be measured. In galaxies like IC 1101, dark matter provides the gravitational glue that holds the galaxy together. Without it, the immense mass and rotation of the galaxy would cause it to fly apart. This invisible scaffolding extends far beyond the visible boundaries of the galaxy, forming an enormous spherical halo that is essential for its structure and stability. Understanding how dark matter influences galaxies on such a grand scale remains one of the foremost goals of astrophysics. The galaxy's location in the Able 2029 cluster adds yet another layer of complexity. Galaxy clusters are teeming environments, full of gravitational interactions, gas exchanges, and potential collisions. These high-density regions are hotbeds of cosmic activity. IC 1101's central position in the cluster suggests it may be the result of multiple central galaxy mergers, a process that often forms what's known as a CD galaxy, a giant elliptical galaxy found at the center of clusters. These galaxies are characterized by their large size, extended halos, and dominant gravitational influence within the cluster. IC 1101 fits this description perfectly. In addition to its gravitational pull, IC 1101 may influence the cluster through its emission of X-rays. The hot, ionized gas surrounding galaxy clusters often emits X-rays, which can be detected by telescopes like Chandra. Observations of Able 2029 show strong X-ray emissions, which helps scientists map the cluster's structure and the distribution of dark matter. IC 1101's presence contributes significantly to this emission, further emphasizing its role as a dominant force in the region. All of these factors, the galaxy's age, its star population, the central black hole, its dark matter halo, and its position in a rich galaxy cluster, paint a picture of a structure that is not only vast in size, but also deeply complex. IC 1101 is not simply a collection of stars. It is a dynamic, evolving system shaped by billions of years of cosmic history. Its characteristics challenge our understanding of the upper limits of galactic formation and provide a unique opportunity to study the interplay of various astrophysical forces on a grand scale. As we continue to observe and model galaxies like IC 1101, we refine our theories of how the universe behaves. Every new piece of data, every insight from simulations, and every photon captured by our telescopes adds to our understanding of the cosmos. IC 1101, with its monumental scale and profound mysteries, stands as one of the most compelling subjects in this ongoing journey of discovery. It reminds us that even in a universe filled with billions of galaxies, there are still giants that stretch the imagination and inspire wonder. Despite its remote distance, over 1 billion light-years away in the constellation of Virgo, IC 1101 continues to reveal information to astronomers who are able to observe it using powerful instruments like the Hubble Space Telescope and the Chandra X-ray Observatory. Its sheer massiveness allows it to exert influence on its surroundings in ways that can be detected across vast stretches of space. For example, its gravitational pull affects the movement of other galaxies in the Able 2029 cluster, warping spacetime around it, and giving rise to observable phenomena such as gravitational lensing. This lensing can bend and distort the light from more distant background galaxies, essentially allowing IC 1101 and its cluster to act like a natural telescope, bringing into view galaxies that would otherwise be invisible to us. This gravitational lensing is not just a curiosity, it's a valuable scientific tool. By analyzing the distortions in background light caused by IC 1101 and the Able 2029 cluster, astronomers can map out the distribution of dark matter, which does not interact with light but still contributes to the gravitational field. These maps help us understand not only the mass of IC 1101, but also the broader dark matter landscape of the cluster it inhabits. The more precise our maps, the better we can test and refine models of the cosmos, particularly those related to dark matter's elusive nature and distribution. There's another key aspect of IC 1101 that captures scientific attention: its age. IC 1101 is believed to be an ancient galaxy, forming relatively soon after the Big Bang. Estimates place its age at over 10 billion years, meaning it has existed for nearly 3/4 of the universe's lifetime. Over this immense stretch of time, IC 1101 has witnessed and participated in cosmic events on a scale that's difficult to comprehend. It has seen stars live and die, black holes form, galaxies collide, and entire structures evolve in the web of cosmic filaments that define our universe's architecture. Its longevity means IC 1101 is a kind of living fossil of the cosmos, an ancient remnant of a time when the universe was more chaotic, hotter, and filled with material waiting to coalesce into stars and galaxies. By studying galaxies like IC 1101, scientists gain insights into the early epochs of galaxy formation. The remnants of those early days are still embedded in IC 1101 structure, in its oldest stars, in its globular clusters, and in the elemental composition of its interstellar medium. All of these aspects offer clues to the conditions of the young universe. In terms of elemental makeup, IC 1101 stars are mostly composed of older, heavier elements, what astronomers call metals, which in this context includes all elements heavier than hydrogen and helium. These metals are produced in the hearts of stars through nuclear fusion and distributed throughout the galaxy when those stars die, particularly in supernova explosions. Over time, successive generations of stars become more metal-rich. However, in IC 1101, most of the stars belong to early generations that formed before many supernovae had time to enrich the interstellar medium. This means that while there are metals present, the galaxy doesn't have as high a metallicity as younger galaxies with ongoing star formation. The stars here are relics of a more pristine, unprocessed universe. This element scarcity contributes to another fascinating fact. IC 1101 is not forming stars at the same rate as younger, more gas-rich galaxies. In many spirals and irregular galaxies, the birth of stars continues actively. These galaxies have thick clouds of gas that collapse under gravity to form new stars in bright, hot nurseries. But IC 1101 is largely quiescent, meaning it's no longer forming stars at any significant rate. This makes it a passive galaxy, filled with aging stars that will eventually burn out, leaving behind white dwarfs, neutron stars, and black holes. The reasons behind this quiescence are many, but among the most prominent is the influence of its central black hole. Supermassive black holes like the one at IC 1101's heart are known to release extraordinary amounts of energy when actively feeding on matter. This process, known as an active galactic nucleus, AGN, can heat or expel the gas within a galaxy, halting star formation by making the gas too hot to collapse into new stars. Though IC 1101's AGN may no longer be active, it likely played a major role in heating and expelling gas during its earlier, more energetic stages. That early feedback would have shaped the galaxy's future, locking it into a state of quiet aging that continues today. It's also likely that IC 1101 has interacted with many other galaxies during its long life. In fact, its enormous size suggests it has absorbed or merged with dozens, possibly even hundreds, of smaller galaxies over billions of years. These interactions are a key feature of galactic evolution. They not only build mass but also drastically alter structure. Spiral galaxies, with their beautiful arms and central bulges, often lose their shape after a major merger. The gravitational chaos of such encounters scrambles the orbits of stars and disrupts gas clouds, transforming orderly spirals into diffuse elliptical giants. IC 1101 is a perfect example of this kind of transformational growth. Some astronomers even theorize that IC 1101 might eventually grow even larger, swallowing nearby galaxies in the Able 2029 cluster. If that happens, it may evolve into an even more massive, supergiant, elliptical, potentially breaking records for galactic size and mass. Such growth would further intensify its gravitational grip on the cluster and possibly alter the cluster's evolution. It would also mean an even greater accumulation of stars, black holes, dark matter, and historical data embedded in its stellar populations. The outer regions of IC 1101 are of particular interest because they contain tidal streams, long, thin structures of stars that are believed to be remnants of smaller galaxies torn apart by IC 1101's gravity. These streams are like fingerprints, marking the passage and consumption of smaller systems. By studying them, scientists can reconstruct the timeline of mergers and interactions that built the galaxy over time. Each stream tells a story, a galaxy once complete and independent, eventually drawn in by IC 1101's irresistible gravity, broken apart, and integrated into the larger whole. Another component contributing to the massive scale of IC 1101 is its stellar halo, a vast, spherical region surrounding the central bulge and extending far beyond the visible edge of the galaxy. This halo is populated by old stars, globular clusters, and a significant amount of dark matter. It's thought that much of this halo formed through the accumulation of debris from past mergers. This component is faint and difficult to detect, but observations indicate that IC 1101's halo is among the largest ever observed, giving it an even more impressive scale than what the eye can see. The implications of such a massive galaxy are not limited to astronomy. They extend into cosmology, the broader study of the universe's structure and history. IC 1101 challenges models of galactic formation, pushing the boundaries of what we believe is possible. If such massive galaxies can exist, and even thrive, in the known universe, we must ask, are there even larger galaxies yet to be discovered? What physical laws, if any, limit the size a galaxy can reach? These questions are part of an ongoing investigation into how matter assembles on the largest scales, how structures evolve over time, and what the fate of such systems might be. Moreover, galaxies like IC 1101 may hold clues to the fate of the universe itself. As galaxies age and star formation ceases, the universe will grow darker, quieter, and colder, a process sometimes referred to as the heat death of the universe. IC 1101, with its immense population of aging stars and dormant interstellar medium, is a glimpse into this potential future. It is what our own Milky Way may look like billions of years from now, quiet, golden-hued, and slowly dimming as its last stars flicker out. Over time, galaxies like IC 1101 essentially become stellar graveyards, vast, sprawling realms where the hustle of star formation has given way to silence and stillness. They glow not with the hot, blue light of new stars, but with the soft, golden hue of aged stellar populations. The light they emit carries the signatures of red giants, aging stars nearing the end of their lifespans, and it is this light, faint, stretched, and ancient, that astronomers rely on to read the story of these cosmic titans. One remarkable aspect of IC 1101 is that, despite its dormancy in star formation, it is still alive with activity in other forms. The core of the galaxy, although not currently considered an active galactic nucleus, almost certainly harbors a supermassive black hole that once flared with incredible intensity. When this black hole was actively accreting material in the past, it would have generated massive jets of particles and radiation that carved out cavities in the surrounding gas, potentially heating vast portions of the galaxy's interstellar and intergalactic medium. These outbursts are thought to play a crucial role in galactic feedback mechanisms, the processes that regulate star formation and influence the growth of galaxies over time. Astronomers have detected evidence of these ancient outbursts in many elliptical galaxies, particularly in massive cluster-central galaxies like IC 1101. Observations in the X-ray spectrum can sometimes reveal bubbles or cavities in the hot gas surrounding such galaxies, remnants of past AGN activity. These bubbles are formed when jets from the black hole push against the surrounding gas, displacing it and creating visible voids. In IC 1101's case, these features are difficult to detect directly due to its distance, but indirect evidence suggests it once possessed the type of energetic core that could leave long-lasting imprints on its environment. And speaking of its environment, the Able 2029 galaxy cluster in which IC 1101 resides is itself a subject of intense study. Galaxy clusters are among the largest gravitationally bound structures in the universe, containing thousands of galaxies, enormous quantities of hot intracluster gas, and staggering amounts of dark matter. IC 1101 sits at the very heart of this cosmic metropolis, anchoring the cluster's gravitational center. This central position is no coincidence. Galaxies like IC 1101 grow large in part because of their privileged placement. They act as gravitational wells, drawing in smaller galaxies, gas clouds, and dark matter, steadily accumulating mass over billions of years. The dynamics of the cluster, how galaxies move, how gas flows, how dark matter is distributed, are all shaped by the massive presence of IC 1101. In this sense, the galaxy isn't just a passive structure drifting through the cosmos, it's an active participant in sculpting the cluster around it. Studies of galaxy clusters like Able 2029 are key to understanding the evolution of large-scale structure in the universe. They help us trace how matter has clumped together since the Big Bang, and how these clumps evolve over time through gravitational attraction and interaction. The hot gas that fills the space between galaxies in Able 2029 is another important element of this cosmic ecosystem. This intracluster medium is composed of ionized particles that emit X-rays due to their extreme temperatures, often tens of millions of degrees Kelvin. X-ray observations allow astronomers to measure the temperature, density, and motion of this gas, which in turn provides insights into the mass and energy dynamics of the cluster. IC 1101, being the dominant galaxy at the cluster's core, plays a central role in heating and stirring this gas through gravitational forces and historical AGN outbursts. Furthermore, the hot gas also acts as a diagnostic tool for detecting the presence of dark matter. Dark matter doesn't emit or absorb light, but its gravitational pull affects the movement and distribution of visible matter. By comparing the observed distribution of hot gas and galaxies with gravitational lensing data, astronomers can infer the presence and density of dark matter in and around IC 1101. These comparisons have led to detailed dark matter maps that show just how massive the core of Able 2029 is, and how IC 1101 sits within one of the deepest gravitational wells ever detected. Let's not forget the awe-inspiring scale of this galaxy. IC 1101 is estimated to span over 400,000 to 500,000 light-years in diameter, nearly 4 to 5 times the diameter of the Milky Way. That's 500,000 years for light to travel from one end of the galaxy to the other. Within this cosmic titan are hundreds of billions of stars, possibly more than 1 trillion if we account for dim and difficult-to-detect stellar populations. If you were to stand on a hypothetical planet orbiting a star in the outer rim of IC 1101 and look up at the sky, you would see an incredibly dense, golden-hued field of stars, stretching across the heavens like a cosmic ocean with no horizon in sight. And while this scale is already almost too much to imagine, it becomes even more astounding when you consider that IC 1101 is just one galaxy among hundreds in Able 2029, and one of trillions in the observable universe. Yet it is among the very largest ever found. That uniqueness adds to its importance. The outliers in nature, whether they're the smallest or the largest, the fastest or the slowest, often teach us the most. IC 1101 is a galactic anomaly that forces us to refine our models, adjust our assumptions, and push our imaginations to greater scales. In fact, one of the fundamental questions surrounding IC 1101 is how it managed to grow so large. The prevailing theory is hierarchical merging, the idea that galaxies grow over time by consuming smaller ones. But even that model struggles to fully explain the enormity of IC 1101. Did it simply have a head start, forming earlier than most and therefore accumulating more mass over time? Did it benefit from an unusually dense environment, with abundant galaxies nearby to merge with? Or could there be other, unknown processes at work, perhaps involving the mysterious behavior of dark matter or exotic physics from the early universe? These questions drive the work of many astrophysicists and cosmologists. Each new observation of IC 1101, each new simulation that tries to replicate its growth, and each new theory that aims to explain its characteristics helps us get closer to understanding the true nature of the universe. The galaxy is not just a giant object in space, it is a cosmic riddle, wrapped in a tapestry of ancient light, and governed by laws we are only beginning to grasp. Yet for all its scientific value, IC 1101 also captures our imagination in ways that defy data. There is something profoundly moving about the idea of a galaxy so vast and ancient, sitting silently in the cold dark of intergalactic space. It has endured cosmic collisions, unleashed unimaginable energy, and consumed entire galaxies. And still it drifts, slowly, at the center of its cluster, glowing with the aged light of 1 trillion stars. What civilizations might have risen and fallen within its countless systems? What stories might its stars tell if they could speak? Could life exist in the vast corners of this ancient behemoth, perhaps evolved under stars very different from our Sun, shaped by histories vastly older than ours? These are questions we may never be able to answer, but that doesn't make them any less worth asking. And as we continue to probe deeper into the enigma of IC 1101, we must grapple with the implications it holds not just for our understanding of galaxy formation, but for the very structure of the universe itself. This massive galaxy, seated at the heart of Able 2029, acts as a gravitational anchor point, and its influence reaches far beyond what we can see with optical telescopes. Light from IC 1101 carries the mark of extreme age, traveling over 1 billion years to reach us, bearing witness to an era of the cosmos that has long since passed. It reminds us that when we gaze at such galaxies, we are not seeing them as they are now, but as they were in a distant epoch, billions of years ago. That concept alone is worth pausing over. The starlight we observe today from IC 1101 left that galaxy when Earth's continents looked different, when dinosaurs still roamed, and when humanity itself had not yet come into being. By the time that ancient light strikes our instruments, the structures that emitted it may have changed dramatically, or even ceased to exist. This time delay turns our view of IC 1101 into a kind of time capsule, a snapshot from the depths of the universe's history. And this is where cosmology and philosophy begin to intertwine. IC 1101 isn't just an object to study, it becomes a reflection of our place in the cosmos. We are looking at a galaxy so large it boggles the imagination, yet it is located so far away that we can only see its ancient echo. It is like looking at the ruins of a long-lost civilization from a mountaintop across a vast, uncrossable valley. The scale and time involved are beyond anything we experience in daily life, forcing us to recalibrate our sense of reality. This kind of perspective-shifting insight is common in astronomy. It humbles us. It reminds us that, no matter how central we believe ourselves to be, we are a tiny part of a far greater whole. IC 1101, with its trillions of stars, its ancient black hole, and its galactic history of collisions and growth, is but one point of light in the deep sky, an extraordinary one, yes, but still only one. And that leads to a profound truth. The universe is not just vast in scale, but also vast in its ability to surprise and surpass our expectations. In many ways, IC 1101 is the universe's reminder that the boundaries we perceive, of size, of age, of influence, are always being redrawn. Just when astronomers think they've found the largest galaxy, or the most massive black hole, or the farthest light, the cosmos unveils something even grander, something that stretches our models and demands we think more boldly. It is through these cosmic outliers that science evolves. And IC 1101 is an outlier of the highest order. Let's now take a deeper look at how IC 1101 interacts with its galactic neighbors. Being at the center of a massive cluster like Able 2029 means that it is not just passively receiving other galaxies, but also actively influencing the dynamics of everything around it. Its gravity pulls on nearby galaxies, distorting their paths, creating tidal interactions, and slowly drawing them in. As these galaxies fall toward IC 1101, they often become elongated and torn apart by gravitational forces, a process called tidal stripping. Their stars and gas are slowly fed into IC 1101's halo, contributing to its immense growth and to the development of a vast envelope of diffuse light that stretches far beyond its visible disk. This diffuse stellar halo, sometimes called the Intercluster light, ICL, is one of the most haunting and beautiful aspects of massive galaxies like IC 1101. It is composed of stars that no longer belong to any single galaxy, stars that have been stripped from their homes and now drift freely through the cluster. These orphan stars, far from the bustling centers of any galaxy, float in a kind of stellar limbo, silent witnesses to the violent history of galaxy formation. They glow faintly in the darkness, a cosmic fog of ancient light that envelopes IC 1101 and contributes to its visual and gravitational dominance. Interestingly, this intercluster light is notoriously difficult to detect. It is faint, often many times dimmer than the night sky, and can only be observed using the most sensitive instruments and careful analysis. But when it is mapped, it paints a portrait of the cluster's dynamic history. The patterns and distribution of this light reveal where galaxies have collided, where they've been torn apart, and where IC 1101 has grown by feasting on the remnants of its neighbors. It is a cosmic archaeology of sorts, with each stream of stars telling a tale of galactic cannibalism and cosmic evolution. The idea of galactic cannibalism, in fact, is central to IC 1101's growth. This process, where large galaxies consume smaller ones, is a fundamental driver of galaxy evolution in the universe. While it might sound violent, it is a natural and common part of cosmic development. In IC 1101's case, this cannibalism has occurred on a massive scale. The galaxy has likely devoured hundreds, if not thousands, of smaller systems over its history. Each time, it has absorbed new stars, new gas, and perhaps even new black holes, further increasing its size and complexity. This leads us to one of the most compelling questions about IC 1101. How massive is its central black hole? Though we cannot yet measure it directly due to the galaxy's distance and the limitations of current technology, extrapolation from similar galaxies suggests that IC 1101's central black hole could be one of the largest in the universe. It is possible, some would say likely, that it harbors a black hole with a mass exceeding tens of billions of solar masses. This would place it in the category of ultramassive black holes, objects so large and powerful that they can influence regions thousands of light years across. Such a black hole would have once radiated with incredible energy, heating and stirring the gas of the cluster, affecting the orbits of nearby stars, and potentially shutting down star formation on a galactic scale. These ultramassive black holes are one of the great mysteries of modern astronomy. We do not fully understand how they grow to such immense sizes. The leading theory is that they start as smaller black holes, left over from massive stars or formed from dense gas clouds, and grow over time by accreting matter and merging with other black holes. But the exact details remain elusive, especially for the largest examples. IC 1101 could hold vital clues. By studying its central regions, by observing the motion of stars near its core and modeling its mass distribution, we might one day determine just how massive this hidden monster truly is. And if the black hole at the heart of IC 1101 is indeed as massive as we suspect, it would not only rewrite the record books, but also challenge our theories of black hole formation. It might suggest that certain regions of the early universe were especially conducive to the rapid growth of black holes, or that some unknown mechanism allowed these cosmic giants to reach their enormous size faster than we currently believe possible. But perhaps most intriguing of all is the question of how IC 1101 will evolve in the far future. Despite its enormous size and relatively static appearance, IC 1101's story is far from over. It still resides in a dense cluster environment, meaning future mergers are likely. As time marches on, more and more galaxies in Able 2029 will fall toward the center, and IC 1101 may continue to grow. Some astronomers speculate that in the distant future, tens or hundreds of billions of years from now, it could become part of a single, massive elliptical galaxy that encompasses the entire core of the cluster. This future galaxy would be unimaginably large, a kind of final resting place for the stars of Able 2029. This eventual outcome, sometimes called a fossil group or CD galaxy phase, represents the endpoint of hierarchical galaxy formation in dense environments. It is the slow, inevitable collapse of a cluster's galaxies into a single behemoth. And in IC 1101, we may already be witnessing the early stages of this process. It is a galaxy that has transcended normal classifications. It is no longer just an elliptical galaxy, it is a growing, evolving cosmic leviathan. And as it continues to grow, its gravitational influence will only increase, further shaping the dynamics of the cluster. It will continue to absorb gas and stars, continue to distort spacetime with its mass, and continue to dominate the cosmic landscape of its region. In this way, IC 1101 is not just a relic of the past, it is a glimpse of the future. It is what happens when galaxies are left to grow, merge, and evolve over unimaginable spans of time. Eventually, IC 1101 may become something even more extreme, a nearly isolated island in an ever-expanding cosmos. To understand how this future might unfold, we need to look not just at the galaxy itself, but at the fate of the universe it inhabits. According to our current understanding of cosmology, the universe is not only expanding, but doing so at an accelerating rate due to dark energy. Over tens of billions of years, this expansion will stretch the fabric of space to such an extent that galaxy clusters will no longer be gravitationally bound to one another. This means that galaxies not tightly grouped together, like those in Able 2029, will gradually fade from each other's view. They won't actually move in the traditional sense. Instead, the space between them will grow so fast that light emitted from them will no longer reach others. Eventually, only galaxies within a given cluster, bound by gravity, will remain visible to one another. Everything else will disappear beyond the cosmic event horizon. In this distant future, IC 1101, now already the dominant force in its region, may become one of the last visible giants in a dark, ever lonelier universe. That future might sound bleak, but it's also awe-inspiring. IC 1101 could be one of the last structures to maintain its grandeur and cosmic relevance in a universe that is gradually growing cold and dark. And because of its location in a dense galactic core, it is one of the lucky ones. It exists in a place where matter has congregated, where galaxies have merged, and where gravitational bonds will remain strong enough to outlast even the universe's relentless expansion. But let's come back to the present and examine how we even discovered IC 1101 in the first place. The galaxy was first identified in the 1980s, thanks to increasingly powerful telescopes and sky surveys that probe deeper into the cosmos than ever before. Its position in the Able 2029 cluster made it particularly interesting to astronomers, as these rich clusters are often home to massive central galaxies. Upon closer inspection, IC 1101 revealed itself to be far larger than expected, both in physical size and luminosity. Early imaging showed a galaxy stretching nearly 400,000 to 500,000 light-years across, depending on how far into its faint outer regions one measures. To put that into perspective, that's about 4 to 5 times the size of the Milky Way. But what's more astonishing is its mass. IC 1101 is estimated to contain over 100 trillion stars. While exact numbers are difficult to pin down due to its distance and faint outer halo, it's clear that IC 1101 dwarfs typical galaxies in nearly every measurable way. These measurements were made possible using instruments like the Hubble Space Telescope, the Sloan Digital Sky Survey, and a variety of ground-based observatories capable of detecting faint light from distant objects. Spectroscopic studies allowed astronomers to analyze the galaxy's redshift, which tells us how fast it is moving away from us due to the expansion of the universe. From this data, we infer its distance, roughly 1.04 billion light-years from Earth. That number is important because it anchors IC 1101 in a specific time in cosmic history. The light we see today began its journey when the universe was about two-thirds its current age. This places IC 1101 in a period when galaxy clusters were well-formed and major mergers were still actively shaping the largest galaxies. The galaxy's appearance during this time gives us a snapshot of what the universe looked like long before our own Milky Way reached maturity. Another intriguing aspect of IC 1101 is its stellar population. Because of its age and its environment, IC 1101 contains mostly old stars, reddish, cooler stars that have long since passed the most active stages of their lives. These stars are typically found in elliptical galaxies, which are generally thought to have stopped forming new stars billions of years ago. In IC 1101, star formation appears to have ceased a long time ago, and much of the gas that could fuel new stars has either been consumed or ejected. This quiescence is likely due in part to feedback from the central black hole. As black holes grow, they can enter an active phase, where they emit enormous jets of energy in the form of quasars or radial lobes. This energy can heat up or blow away gas within the galaxy, making it harder for that gas to cool and collapse into new stars. In massive galaxies like IC 1101, this feedback process can be so powerful that it effectively ends star formation altogether, locking the galaxy into a state of slow aging. And yet, despite this quiet phase, IC 1101 continues to evolve. Its outer regions may still be accreting stars and dark matter from its surroundings. In fact, one of the great mysteries about IC 1101 is the nature and distribution of its dark matter halo. Like all large galaxies, IC 1101 is embedded in a vast, invisible cloud of dark matter, an unknown substance that exerts gravity but does not emit or absorb light. This dark matter is believed to be critical to the formation and stability of galaxies, and in the case of IC 1101, it likely extends far beyond the visible boundaries of the galaxy itself. Models suggest that IC 1101's dark matter halo could stretch for millions of light-years and contain many times the mass of its visible stars. This halo helps explain how the galaxy maintains its structure, how it attracts and absorbs other galaxies, and how it fits into the larger framework of the Able 2029 cluster. Yet we still know very little about the exact properties of this dark matter. Is it clumpy or smooth? Does it interact only through gravity, or are there other forces at play? By studying IC 1101 and galaxies like it, we hope to answer these questions in the coming decades. And let's not forget that IC 1101 is more than just a giant, it is a keystone in our understanding of the cosmic web. The universe is not a random scattering of galaxies, but a vast, interconnected structure of filaments, clusters, and voids. Galaxies form where these filaments intersect, where matter is densest. IC 1101 occupies one such node, acting as a marker for where gravity has done its work most effectively. It is a monument to cosmic structure, an architectural relic built by the forces that shape the universe. Every aspect of IC 1101, from its central black hole to its intercluster halo, tells a part of the story of how structure arises in the universe. And this story isn't limited to one galaxy. By studying IC 1101, astronomers can refine their models of galaxy formation, test theories about black hole growth, understand the behavior of dark matter, and trace the history of star formation across cosmic time. In essence, IC 1101 is a cosmic classroom, a place where nature's most complex processes are laid bare for us to explore. Even its position in the Able 2029 cluster offers insights into cosmic evolution. This cluster contains hundreds of galaxies, all gravitationally bound, all orbiting a common center of mass. The dynamics of this cluster, the interactions among its members, the temperature and distribution of its hot gas, and the role played by IC 1101 in holding it all together, these are the subjects of intense study. Astronomers use radio telescopes to detect emissions from the cluster's gas, X-ray observatories to probe its energetic core, and optical surveys to map the distribution of its galaxies. Through all these layers of investigation, IC 1101 stands at the heart, silent, massive, and revealing. It is also worth considering how IC 1101 challenges many of the traditional boundaries we've assigned to galaxies in terms of classification. While the Hubble sequence typically divides galaxies into spirals, ellipticals, and irregulars, IC 1101 stretches the definition of a giant elliptical galaxy to a point where it almost deserves its own category. Most elliptical galaxies are already massive and old, but IC 1101 is on an entirely different scale. Its luminosity profile doesn't fall off as quickly as smaller ellipticals, and its extended halo of stars and intracluster light indicates a galaxy whose outskirts blend into the intergalactic medium in a way that's rarely seen. This phenomenon of intracluster light, stellar light not bound to any one galaxy but drifting freely within the cluster, is particularly fascinating. In the environment around IC 1101, stars have likely been stripped from smaller galaxies as they were absorbed, their orbits stretched and smeared across tens or even hundreds of thousands of light years. This creates a diffuse, ghostly glow around IC 1101, contributing to its colossal apparent size and giving us clues about its violent past. These orphan stars are the remnants of galactic collisions, the faint signature of cosmic cannibalism etched into the fabric of space. The role of IC 1101 in this environment is akin to a gravitational anchor. Smaller galaxies that venture too close are subjected to immense tidal forces. Their outer stars are ripped away, their gas compressed or ejected, and their cores gradually pulled inward until they become part of the larger whole. Over billions of years, this process smooths out any remaining structure, contributing to IC 1101's featureless, spheroidal appearance. But even in its apparent simplicity, IC 1101 is not uniform. When observed at high resolution, subtle features emerge, gradients in metallicity, where the abundance of heavier elements changes with radius, varying densities of stars, indicating a complex assembly history, and signs of past interactions, such as shell-like structures or faint tidal streams. These details help astronomers reconstruct the sequence of events that led to IC 1101's current state. Like tree rings in an ancient forest giant, the faint ripples and stellar gradients of IC 1101 tell a story of growth, mergers, and time. The metallicity of IC 1101 is another vital clue to its evolution. In galactic terms, metals refer to any element heavier than helium, produced in the cores of stars and distributed into space by supernovae and stellar winds. The more metals a star or gas cloud contains, the more generations of star formation it has experienced. In IC 1101, the core is rich in metals, suggesting that it has undergone many cycles of star birth and death. However, the outer regions are relatively poor in metals, pointing to their origin in smaller, less evolved galaxies that were absorbed during mergers. This gradient in composition is like a fossil record of galactic consumption. And what about the stars that remain? The stars of IC 1101 are mostly old, but not entirely homogeneous. There is evidence of different populations, some perhaps as old as 10 to 12 billion years, dating back nearly to the dawn of galaxy formation, and others slightly younger, maybe 6 or 7 billion years old, from more recent acquisitions. These populations vary in age, motion, and chemical composition, forming a layered portrait of cosmic history embedded within a single structure. The dynamics of IC 1101 stars are also telling. Unlike spiral galaxies, where stars follow relatively ordered, circular orbits, the stars in IC 1101 move in a more random fashion, following elliptical and chaotic paths around the galactic center. This is typical for elliptical galaxies, which lack the flat, rotating disk structure of spirals. The randomness of the star's orbits contributes to the galaxy's rounded shape and is a direct consequence of the violent mergers that built it. Each collision scrambled the motions of stars, creating a structure that is more pressure-supported than rotation-supported. Despite its size, IC 1101 is surprisingly dim in terms of star formation. While the galaxy emits a great deal of light, it does so primarily from aging stars rather than the bright, young blue stars seen in star-forming galaxies. The cold gas needed to form new stars is largely absent, either heated to extreme temperatures by mergers and black hole activity, or expelled into intergalactic space. In this sense, IC 1101 is a galactic graveyard, where the echo of creation remains visible, but the process itself has all but ceased. Yet, it may not be entirely dead. There are hints of low-level activity, faint emissions in certain wavelengths that suggest occasional interactions with smaller galaxies or the presence of some residual gas. It's possible that IC 1101 experiences minor star formation in isolated pockets, or that future mergers could reintroduce enough gas to spark brief starbursts. However, given its current state and environment, these would likely be rare and short-lived. One cannot discuss IC 1101 without returning to its supermassive black hole. Though not directly observed, the size of its central bulge and the mass of the galaxy suggest a black hole of immense proportions. Some estimates place it in the range of tens of billions of solar masses, potentially among the most massive ever conceived. This black hole would dominate the inner region of the galaxy, influencing the orbits of stars, heating surrounding gas, and shaping the evolution of the galactic core. If this black hole were active, it could produce powerful jets of energy, visible in radio waves or X-rays, stretching for hundreds of thousands of light years. In its current state, IC 1101 does not appear to host such jets, suggesting that the black hole is either dormant or only weakly active. But that could change. A new influx of matter, perhaps from a cannibalized galaxy, could reignite the central engine, turning IC 1101 into a beacon once more. That possibility remains tantalizing, for it reminds us that even the quietest giants are capable of sudden drama. In the cold and static reaches of the intergalactic void, a spark from IC 1101's core could light up the sky once more, sending out ripples of energy that would travel for millions of years before reaching us. Such events may be rare, but they are not impossible, and astronomers continue to monitor similar galaxies for signs of reactivation. IC 1101's influence even extends to gravitational lensing, a phenomenon where the galaxy's immense mass bends the light of background objects. This effect, predicted by Einstein's general relativity, has become a powerful tool in modern astronomy. In galaxy clusters like Able 2029, gravitational lensing allows us to map the distribution of dark matter and study galaxies far beyond the reach of our telescopes. IC 1101's gravitational field, therefore, acts not only as a cosmic anchor, but also as a magnifying glass, offering glimpses of the distant universe through its powerful lens. This capacity to affect and reveal distant light underscores the importance of studying IC 1101 not just for its own sake, but as a gateway to understanding the cosmos itself. It is a laboratory for extreme physics, a testing ground for gravitational theory, and a record keeper of galactic history. It offers answers to questions we have barely begun to ask and challenges assumptions we have long held as truth. As telescopes become more powerful, like the James Webb Space Telescope and future observatories like the Extremely Large Telescope, ELT, we will continue to refine our picture of IC 1101. New data will allow us to probe its faintest regions, detect subtle changes in its core, and trace the trajectories of its constituent galaxies. We may even discover companion black holes, hidden populations of stars, or unexpected features in its structure. Every new discovery will add another layer to our understanding of this colossal entity. We must also reflect on the scale of time involved in IC 1101's journey through the cosmos. It was not born in a day, nor even in a billion years. Its current form is the product of more than 12 billion years of cosmic evolution, an almost unimaginable span of time. Galaxies like IC 1101 represent the culmination of processes that began shortly after the Big Bang. Gravity, that most patient of sculptors, has pulled matter together, merged systems, and shaped the universe into what we observe today. In this context, IC 1101 is not just a structure, it is a story, written across billions of years in the language of stars, gas, and dark matter. This long evolution raises profound philosophical questions as well. If galaxies are born, grow, age, and eventually fade, then they too are subject to the cosmic cycle of life and death. What, then, does the eventual death of IC 1101 look like? Not a sudden collapse or fiery explosion, but a slow fading, its stars aging into red dwarfs and white dwarfs, its gas consumed or expelled, its black hole growing quietly in the center. Over trillions of years, IC 1101 will gradually become darker, colder, and more diffuse, a ghost of its former self drifting through an ever-expanding universe. In the distant future, galaxies like IC 1101 may no longer be visible at all. Due to the accelerating expansion of the universe, driven by dark energy, galaxies beyond our local group are moving away from us at ever-increasing speeds. Eventually, they will recede beyond the cosmic event horizon, the point beyond which light can never reach us. IC 1101, if it has not merged or faded into obscurity, will one day slip into this unreachable realm, leaving behind only the light that has already been emitted. That light will continue to travel through space, a final echo of a giant we will no longer be able to see. This thought alone places IC 1101 in a special category of cosmic wonders. Not only is it a record of ancient processes, but it is also a fleeting glimpse into a realm we may never witness again. It is the past and the future, the known and the unknowable. To look upon IC 1101 is to see what once was and what may never be again. But how do we know all of this? How do we, from our tiny planet orbiting an unremarkable star, come to understand the structure and history of a galaxy over a billion light-years away? The answer lies in the triumph of human curiosity and the tools we've built to satisfy it. Telescopes, spectrometers, and observatories, spanning Earth and space, have enabled us to collect photons that have traveled across vast stretches of the universe. With these instruments, we decipher the composition, motion, and properties of distant galaxies. IC 1101 speaks to us not with sound or voice, but with light, and we have learned to listen. Spectroscopic analysis allows astronomers to break down the light from IC 1101 into its component wavelengths, revealing information about the stars and gas it contains. From the redshift of its spectral lines, we know its distance. From the absorption features, we determine its metal content. From the broadening of lines, we infer the motion of stars. These techniques, refined over decades, have turned light into a tool of cosmic archaeology. With each new observation, we peel back a layer of time and deepen our understanding of how such galaxies come to be. And still, for all we know, IC 1101 remains deeply mysterious. Its full extent may not yet be known. Many of its stars fly so far from the core that they blend into the intergalactic medium. Its halo may be larger than current models suggest. Its black hole may be more massive, its dark matter distribution more complex. Each time we believe we've reached the limits of our understanding, new data redefines those limits, reminding us that even the most studied objects in the cosmos still hold secrets. There's also the question of environment. Why IC 1101, and not another galaxy, became so large? Its location at the center of a rich cluster like Able 2029 is a major factor, but that alone does not guarantee such size. The exact timing of its mergers, the composition of its galactic prey, the initial density of its surroundings, these are all variables in a complex equation. IC 1101, then, is not just a product of favorable conditions, it is the result of cosmic luck, of statistical rarity, of paths taken and not taken. It is, in every sense, unique. This uniqueness should be appreciated. Among the hundreds of billions of galaxies in the observable universe, IC 1101 stands out. It is not just large, it is the largest known in terms of visible size and stellar extent. That singular status makes it a natural target for study, but it also imbues it with symbolic significance. It is a monument to the extremes of nature, a boundary-pushing entity that forces us to reconsider what is possible. And what does this mean for us? In contemplating IC 1101, we are reminded of our place in the universe, not as masters, but as observers, not as rulers, but as participants. We are made of the same atoms forged in stars, subject to the same physical laws, traveling on a planet orbiting a star that is one of hundreds of billions. Yet we are capable of comprehending, at least in part, the structure and history of something as vast as IC 1101. That ability is extraordinary. It is a testament to the power of thought, of science, and of imagination. This galaxy, though silent and distant, speaks volumes. Its light has traveled more than 1 billion years to reach us, carrying with it messages about formation, destruction, age, and time. In decoding those messages, we gain not only knowledge but perspective, a sense of the vast tapestry into which we are woven. The continued observation and study of IC 1101 will undoubtedly yield more discoveries. With next-generation telescopes, we may map its halo in unprecedented detail, detect its influence on surrounding dark matter, and probe its core for signs of black hole activity. These efforts will deepen our understanding not only of IC 1101 but of the universe itself, for in the particular, we find the universal. Every galaxy has a story, and IC 1101's is one of the most compelling. We may also use IC 1101 as a benchmark. As we discover other massive galaxies in the future, we will compare them to IC 1101, asking how they differ, why one grew larger or remained smaller, what environmental or historical factors influenced their development. In this way, IC 1101 will continue to guide our study of galactic evolution, even if we one day find a galaxy that surpasses it in size or mass. And what if we do? What if somewhere out there, beyond the reach of our current instruments, lies a galaxy even larger, colder, darker, more ancient? That possibility is both thrilling and humbling. It means that our journey of discovery is far from over, that the universe always has more to reveal. IC 1101, then, is not just an endpoint, it is a beginning, a reminder that the cosmos is vast, and our understanding is always expanding. So the next time you look up at the night sky, think of IC 1101. Though invisible to the naked eye, it exists, a cosmic leviathan drifting silently through the void, a relic of a bygone age, a monument to the grandeur and mystery of the universe. And in that thought, you connect to something greater than yourself, a story written in starlight, etched across billions of years, waiting to be told. The tale of IC 1101 continues to unfold not just in the observable data we collect but in the theoretical models we refine. It is a galaxy that pushes the boundaries of our understanding, compelling us to ask deeper questions about cosmic structure formation and the role of galactic mergers in shaping the universe's most massive entities. One must appreciate how, with each new discovery about IC 1101, we are forced to refine our models of hierarchical clustering and gravitational dynamics. This single galaxy, colossal, brilliant, and ancient, serves as a case study that tests the limits of what our equations and simulations can predict. As we continue probing its luminous outskirts, we find that IC 1101 defies the typical profiles we expect in galaxies. Standard elliptical galaxies exhibit a surface brightness that falls off in a predictable exponential, or de Vauquelins profile. Yet IC 1101's extended halo deviates from these norms. The faint light that stretches out beyond a million light-years challenges how we think about galactic boundaries. Where does a galaxy end? When do its outer stars become intergalactic? IC 1101 blurs those lines, suggesting that galaxy formation is a process not so easily constrained by our conventional definitions. This immense stellar envelope may be composed of orphan stars, stellar remnants flung into deep space during past collisions. Such stars are not gravitationally bound in the same way as those in a dense galactic core, and their presence offers a haunting glimpse into the violence of IC 1101's formation history. Each of these stars, twinkling in the far edges of this behemoth, could represent a solar system ejected from its parent galaxy billions of years ago. The image is staggering: entire suns flung into intergalactic solitude, orbiting a common galactic center so distantly that their light becomes part of a faint, ghostly glow. This outer region is also fascinating from a dark matter perspective. Because stars in this region move slowly and follow extended orbits, astronomers can use their motion to probe the distribution of invisible mass. Current models suggest that the dark matter halo of IC 1101 is proportionally larger than that of typical galaxies, extending far beyond the luminous limits of the galaxy itself. This indicates that IC 1101 sits in a massive gravitational well, one shaped not just by visible matter but by a vast halo of unseen substance. Understanding this halo provides critical insights into the cosmic scaffolding that holds the universe together. The presence of such a massive halo also hints at IC 1101's role in the evolution of its cluster, Able 2029. As the central dominant galaxy, it anchors the cluster both gravitationally and dynamically. The motions of satellite galaxies within the cluster are influenced by IC 1101's gravitational pull, and in turn, their interactions contribute to the ongoing growth of the giant. This reciprocal relationship, where the cluster shapes the galaxy, and the galaxy shapes the cluster, is a cosmic dance millions of years in the making. IC 1101 is not just a passenger in its environment, it is a shaper of it. Zooming in toward its core, we confront the fascinating question of IC 1101's supermassive black hole. While not directly measured with precision due to its distance, estimations based on its stellar mass and central velocity dispersion suggest a black hole mass well into the tens of billions of solar masses, perhaps even approaching 40 billion solar masses. If confirmed, this would make it one of the most massive black holes in the known universe. And with such mass, we are forced to ponder the processes that allowed a black hole to grow so large. Was it through steady accretion of gas? Through the merging of other black holes during galactic collisions? Or could there be more exotic mechanisms at play? This central black hole would have once powered an extraordinarily luminous quasar, a beacon of radiation so powerful it would have outshone the entire galaxy. That quasar may now be dormant, having exhausted the supply of infalling matter. But even in silence, the black hole persists, shaping the motion of stars in the inner core and influencing the galactic dynamics. It also contributes to what's known as AGN feedback, the process by which radiation and outflows from a black hole heat up surrounding gas and suppress further star formation. In a galaxy as evolved as IC 1101, such feedback likely played a crucial role in halting new star birth, turning the galaxy into a massive stellar graveyard where no new stars have formed for billions of years. Yet even in this apparent quiescence, IC 1101 is alive in a different way. The stars it contains, numbering in the hundreds of trillions, each have their own stories. Red giants swell and fade. White dwarfs cool in silence. Some stars orbit peacefully, while others are caught in chaotic elliptical paths through the galaxy's heart. And among them may be planets, and on some of those planets perhaps oceans, clouds, or even the rudiments of life. We will never know for sure, but the possibility adds another layer of depth to our understanding. IC 1101 isn't just a galaxy, it's a universe unto itself. The more we learn, the more we realize that IC 1101 may not be the final word in galactic extremes. There could be galaxies even larger, lurking at the edge of the observable universe or cloaked behind dust and gas. But for now, IC 1101 stands as a cosmic pinnacle, a benchmark for size, structure, and historical complexity. And by studying it, we gain not only facts and figures but perspective. Perspective that tells us how small we are, yes, but also how wondrous it is that we can know so much. From this speck of a planet, we can measure light from across 1 billion light-years, infer the presence of stars and dark matter, model collisions and feedback mechanisms, and piece together the biography of a galaxy so far removed from our own experience that it seems almost mythic. This is the power of science, not just to explain, but to elevate. In IC 1101, we see the grandeur of what the universe can produce given enough time, gravity, and silence. We see the relics of a cosmic era that predates our solar system, our planet, even our elements. We see, perhaps, a glimpse of our own galaxy's far future, a fate of mergers and evolution that may one day transform the Milky Way into a central giant of its own cluster. And we also see a mirror, not of our physical selves, but of our intellectual ambition. We have reached across the cosmos with telescopes and theory to understand something so impossibly vast. That pursuit, quiet, persistent, and magnificent, is one of the highest expressions of human curiosity. And the story continues. Even as we dive deeper into the structure and secrets of IC 1101, we begin to realize that its sheer mass and scale are not anomalies of nature, but instead are natural consequences of the universe's own laws playing out over cosmic time. It is a behemoth born from billions of years of gravitation, momentum, mergers, and starlight. To truly understand IC 1101, we must dive into the fabric of galactic formation and the larger-scale structures that shape the universe. Because galaxies do not exist in isolation, they are nodes in a colossal cosmic web, stretching for billions of light-years, where filaments of dark matter and clouds of gas thread the void and feed galaxy clusters like Able 2029. The location of IC 1101 at the heart of the Able 2029 cluster is no coincidence. Clusters like Able 2029 are gravitationally bound collections of hundreds to thousands of galaxies, all orbiting a common center of mass. Over billions of years, interactions between these galaxies lead to tidal stripping, mergers, and cannibalization. The central galaxy, often referred to as the brightest cluster galaxy, BCG, becomes a gravitational sink, growing larger as smaller galaxies fall into it. IC 1101 is the result of such relentless accumulation, and it's likely that it has devoured dozens, if not hundreds, of smaller galaxies. When one galaxy collides with another, stars don't typically crash into each other because of the immense distances between them. But the gravitational effects are profound. Stars are pulled into new orbits, galaxies are distorted, and gas clouds are shocked, igniting bursts of star formation, though in the case of IC 1101, this process occurred in the distant past. These collisions are not brief either. A single galactic merger can take hundreds of millions of years. Over time, this violent ballet leads to the smooth, featureless appearance of a giant elliptical galaxy like IC 1101. This transformation into a massive elliptical galaxy also signals a change in the galaxy's life cycle. Spiral galaxies like the Milky Way are rich in gas and dust, the raw materials for new stars. They are often sites of ongoing star formation, glowing with young, hot blue stars. Elliptical galaxies like IC 1101, however, are predominantly composed of older, redder stars. They have little gas or dust, having either consumed or expelled it during their violent histories. This is why IC 1101 is sometimes called a red and dead galaxy, not because it's lifeless, but because it no longer forms stars. The ancient stellar population of IC 1101 is a time capsule. These stars are predominantly low-mass, long-lived red dwarfs, and the more massive stars that once existed likely exploded as supernovae billions of years ago. Their remnants, neutron stars, white dwarfs, and possibly black holes, are scattered throughout the galaxy, silent markers of a once fiery youth. Each one tells a story of the chemical evolution of the galaxy, as heavier elements forged in stellar cores and supernova explosions were recycled into subsequent generations of stars. Spectroscopic analysis of IC 1101's light reveals a high metallicity, which refers to the abundance of elements heavier than hydrogen and helium. This is consistent with a galaxy that has undergone numerous cycles of star formation and destruction. The more generations of stars a galaxy has experienced, the more enriched it becomes in metals. This enrichment can also be traced through the color of the galaxy. Redder galaxies tend to have older and more metal-rich stars. IC 1101's color and spectrum both point to its ancient, metal-rich, and evolutionarily mature status. Now let us consider IC 1101's gravitational influence. With a mass of perhaps 100 trillion solar masses or more, IC 1101 exerts an incredible gravitational force. This force is what binds its stars, globular clusters, and even satellite galaxies in orbit around it. But it also affects the hot, ionized gas that permeates the cluster. Observations in X-ray wavelengths reveal that Able 2029, and IC 1101 in particular, are surrounded by vast clouds of extremely hot gas heated to millions of degrees by the gravitational energy of infalling material. These X-ray observations, made by space telescopes like Chandra and XM Newton, allow astronomers to study not just the visible matter, but also the invisible, dark matter. Because hot gas follows the gravitational pull of the cluster, and because the visible mass is not enough to explain the motion and temperature of this gas, we infer the presence of dark matter. IC 1101's own dark matter halo likely comprises a significant portion of its total mass, extending well beyond the visible extent of the galaxy. But what is dark matter? Although we cannot see it, touch it, or interact with it in the traditional sense, its presence is undeniable. It reveals itself through its gravitational influence, in the rotation curves of galaxies, in the bending of light via gravitational lensing, and in the structure of the cosmic web. IC 1101, by serving as a gravitational anchor in its cluster, helps us to map out this elusive dark component of the cosmos. When background galaxies are distorted by its mass, we are given indirect but powerful evidence of dark matter's footprint. Gravitational lensing by IC 1101 and Able 2029 also offers a window into deep time. The warped light from galaxies billions of light-years behind the cluster is bent, magnified, and smeared into arcs and rings, cosmic mirages that tell us not only about IC 1101 itself, but also about the structure of the universe far beyond it. By studying these lensing effects, astronomers can refine models of dark matter distribution, estimate the expansion rate of the universe, and even search for the faintest galaxies at the edge of visibility. The notion of expansion brings us to another fascinating implication. IC 1101 exists at a redshift of about c equals 0.077, which places it roughly a billion light-years from Earth. That means the light we see from it today left the galaxy when the Earth was still in the throes of its last supercontinent cycle. But because the universe is expanding, IC 1101 is actually far more distant now, probably about 1.1 billion light-years away. This raises a fundamental point: we never see the universe as it is, only as it was. IC 1101, as we know it, is a ghost, an ancient image printed on the canvas of space-time. This temporal dislocation inspires awe. For all we know, IC 1101 may have changed dramatically in the billion years since its light began its journey to us. It may have merged with another massive galaxy, igniting a renewed burst of activity. It may have been affected by powerful gravitational interactions. It may even have begun to decay, losing some of its halo stars, or satellite galaxies. But we won't see that change for another billion years. In the same way, civilizations across the cosmos could be watching the Milky Way as it once was, seeing the dinosaurs walk, or the ocean's first form, a humbling reminder of our place in the temporal theater of the universe. Despite its vast scale and ancient age, IC 1101 is not immortal. Galaxies evolve, and their destinies are shaped by the cosmic environment in which they reside. One day, perhaps tens or hundreds of billions of years from now, IC 1101 may cease to resemble a galaxy at all. As its stars die out, as it consumes or loses what little interstellar material it has left, it may become a faint, fossilized remnant, a shadow of its former brilliance. In a far future universe, devoid of new star formation and dominated by dark energy, IC 1101 might be one of the last beacons of stellar light. And what of its stars? Over such vast timescales, even the most stable stars will evolve. Red dwarfs will continue to burn for trillions of years, but eventually they too will dim. White dwarfs will cool into black dwarfs, theoretical objects so cold and faint they emit no light. Black holes will evaporate via Hawking radiation over unimaginably long timescales. The grand, glittering core of IC 1101 will become cold, dark, and silent. But today, in our time, IC 1101 still shines. It stands as one of the greatest achievements of gravitational engineering the universe has ever produced. A monument to time, gravity, and silence. A puzzle box of stars and darkness. A cathedral of ancient light. The continued existence and radiance of IC 1101 carries profound implications not just for astronomy, but for our understanding of the universe's own nature, how matter behaves on grand scales, how time sculpts structures of complexity, and how even in a vast cosmic void, beauty can emerge from chaos. This galaxy is a testament to the power of accretion, of gravity acting unceasingly over eons, slowly building an island of 100 trillion stars where once there may have been only formless gas and dark matter halos. And it's here, at the center of Able 2029, that IC 1101 performs its silent duty. It holds its place at the gravitational heart of its cluster, orchestrating the cosmic motions of hundreds of neighboring galaxies, acting as a keystone to their dynamic equilibrium. It is not a passive observer. It is an active participant in the ever-evolving structure of the cluster. Its mass warps space, its influence governs the thermal state of intercluster gas, and its past dictates the future trajectories of galaxies around it. But how do we observe and confirm these incredible details about IC 1101, a galaxy more than 1 billion light-years away? The answer lies in a symphony of telescopic technology, ground-based optical telescopes that provide high-resolution imaging, radio observatories that detect neutral hydrogen and synchrotron emissions, infrared space telescopes that peer into ancient, dust-shrouded corners, and X-ray observatories that expose the hot, violet plasma halos cloaking the galaxy and cluster. Each telescope contributes a layer of understanding, and together they reveal a multidimensional portrait of this titanic system. The visible spectrum only scratches the surface. Much of what makes IC 1101 so fascinating lies outside the range of human sight. In the radio part of the spectrum, astronomers have detected diffuse emissions suggestive of aged synchrotron radiation, a byproduct of relativistic electrons spiraling in magnetic fields. These emissions are relics of past activity, possibly from powerful jets emitted by supermassive black holes during a more active phase of the galaxy's life. Indeed, lurking in the very core of IC 1101 is almost certainly a monster, a supermassive black hole weighing in at several billion solar masses. Supermassive black holes are not just endpoints of gravitational collapse. They are engines of galactic evolution. During active periods, they can accrete massive quantities of gas and dust, generating tremendous energy in the form of radiation, particle jets, and galactic winds. This energy can heat surrounding gas to such high temperatures that it prevents further star formation, a process known as feedback. In this way, black holes can regulate the growth of their host galaxies. While IC 1101's black hole may now be dormant, the imprints of its past activity are likely still visible in the structure of the galaxy's core and in the high-energy emissions detected across multiple wavelengths. Consider the light profile of IC 1101. Unlike smaller elliptical galaxies, its brightness does not decline smoothly with distance from the center. Instead, it shows a so-called core profile, a flattening of brightness near the nucleus, which is consistent with galaxies that have undergone repeated mergers involving supermassive black holes. When two galaxies merge, their central black holes eventually coalesce, and in the process, they eject stars from the central regions through gravitational slingshot effects. The result is a diffuse, depleted core, a cosmic scar from an ancient collision. The presence of such a core suggests that IC 1101 has endured numerous major mergers, possibly even among the most violent known in the observable universe. Some simulations have suggested that only galaxies that have undergone dozens of major dry mergers, those involving galaxies lacking in gas and dust, can grow to the titanic scales of IC 1101. These events are slow, silent, and majestic. Galaxies interweave, stars change paths, black holes spiral toward one another, and the stellar population becomes ever more mixed and diffuse. But despite the violence of its past, IC 1101 now rests in what seems like cosmic peace. Its current shape is that of a massive elliptical, extending over 400,000 light-years in diameter, more than 4 times the diameter of the Milky Way. It hosts countless billions of stars, globular clusters, possibly hundreds of satellite galaxies, and vast reservoirs of old stellar populations. If one were to stand on a planet orbiting a star deep within IC 1101's core, the night sky would be ablaze with light, not just from nearby stars, but from the close-packed density of stars in every direction. Such a night would dwarf anything ever seen from Earth. The color of IC 1101 is also telling. It shines with a golden yellow hue, the mark of a mature, aged galaxy. This is no realm of hot, young, blue stars or star-forming nebulae. This is a realm of ancient suns, red giants, and dim, dying stars. The light we see today comes from stars that are, on average, several billion years old, relics from an earlier, more active cosmic era. The absence of new star formation means IC 1101's stellar population is aging in place, cooling, dimming, but persisting over extraordinary spans of time. As with all things in the universe, however, IC 1101 is bound to change. Though it may seem static on human timescales, galaxies evolve continually. The surrounding galaxies in Able 2029 are slowly falling toward its gravitational well. One by one, they will spiral inward, merge, and add their stars to its colossal halo. Over the next several billion years, IC 1101 may double in mass, becoming not just the largest known galaxy, but perhaps the central core of a future superstructure, a protocluster core so vast it stretches across millions of light-years. Even more fascinating is the role that IC 1101 plays in cosmological studies. As one of the largest galaxies ever discovered, it acts as a benchmark for simulations of large-scale structure formation. Cosmologists use it as a test case. Can our theories of galaxy formation explain such titanic structures without violating the known laws of physics? So far, the answer is yes, but only just. IC 1101 sits at the very edge of what models predict is possible. Its existence pushes the boundaries of cosmology and provides a real-world counterpoint to theoretical models developed in supercomputers. Moreover, IC 1101's environment is key. Its placement at the center of a rich, massive cluster is no accident. Galaxy clusters like Able 2029 form at the intersection of cosmic filaments, vast tendrils of dark matter and gas that funnel galaxies together. These intersections, or nodes, are the sites of the most extreme matter accumulation in the universe. They are where galaxies collide, where stars are born and die in colossal numbers, and where gravity reigns supreme. In this context, IC 1101 is a natural consequence of the universe's geometry, a masterpiece painted by time and gravity in the very center of a cosmic web. As such, IC 1101 is more than just a galaxy. It is a symbol of the scale of the universe, of the power of gravity, of the long arc of cosmic evolution. It is a monument to billions of years of structure formation, an artifact of the universe's deepest processes. And as we study it, observe it, and reflect on its enormity, we are reminded that even in the vastness of space, patterns emerge, structures form, and from the simplest of beginnings, complexity arises. We see in IC 1101 a mirror of the universe itself, vast, old, mysterious, and brimming with untold stories. The very existence of IC 1101 invites us to ask questions not just about its own past, but about the ultimate future of galaxies and the universe itself. How long can a galaxy this massive maintain its structural integrity? Will it eventually fall into a state of total stasis, where no new stars form, no mergers occur, and all matter simply drifts in a sea of cosmic entropy? Or will it be consumed by even larger structures, such as superclusters or the speculative, dark galaxies of the far future? To answer such questions, we must peer even deeper into the fundamental components that make up IC 1101. Beyond its visible light, beyond its hot plasma halo, and even beyond its supermassive black hole, lies something even more elusive: dark matter. IC 1101, like all galaxies, is embedded in a massive halo of this invisible substance. Though it neither emits nor absorbs light, dark matter makes up the majority of the galaxy's mass. Without it, the stars of IC 1101 would fly apart like leaves in the wind. Dark matter's gravitational pull binds everything together and gives IC 1101 its coherent, stable form. Astronomers measure this dark component not by direct observation, but through its gravitational effects. By analyzing the way stars orbit in the outer reaches of the galaxy, and by observing how light from background galaxies is bent as it passes near IC 1101, scientists can infer the distribution of dark matter. These methods have revealed that IC 1101's total mass may be over 100 trillion times that of the Sun, the vast majority of which is composed of dark matter. This immense gravitational well is what allows IC 1101 to sit so dominantly at the heart of Able 2029, acting as both anchor and arbiter of motion for nearby galaxies. Even the hot gas enveloping the cluster owes its temperature to the gravitational influence of IC 1101 and its neighbors. As intergalactic gas falls into the cluster's deep potential well, it accelerates and compresses, heating up to tens of millions of degrees. This gas emits X-rays, which astronomers can detect using specialized space telescopes like Chandra and XMM Newton. The resulting images reveal glowing clouds that stretch across millions of light years, the breath of a galaxy that, although ancient and silent, still exerts influence on its surroundings. One of the more surreal questions we might ask is what it would be like to travel to IC 1101. Located more than 1 billion light-years from Earth, such a journey would take us through vast stretches of near-empty space. We would pass countless other galaxies along the way, each one containing billions of stars, and each moving through the universe in its own cosmic dance. When we finally approach the Able 2029 cluster, we would begin to see the signs of its immense gravity: galaxies moving faster, light bending in arcs, and the subtle shift in the cosmic background radiation caused by the Sunyaev-Zeldovich effect. Upon arriving near IC 1101, the view would be overwhelming. It would fill the sky, a brilliant and endless stretch of stars. Unlike the Milky Way, which has a thin disk and a bright center, IC 1101 would appear more diffuse, a golden halo stretching far beyond what our eyes could normally process. And yet, in that light lies the history of the cosmos. Each photon would have traveled over 1 billion years to reach us, a message from the distant past, carrying the whispers of ancient stars and the legacy of galactic collisions. The stellar populations of IC 1101, too, are a fascinating study. Unlike spiral galaxies, which host regions of active star formation, IC 1101 stars are mostly old and red. These are stars that formed long ago, during the galaxy's most active periods. Their composition reveals clues about the history of the universe. The ratios of hydrogen, helium, and heavier elements tell us how many generations of stars have lived and died there. From this data, we learn that IC 1101 experienced a rapid period of star formation early in its life, followed by long epochs of passive evolution. In essence, it grew fast and now ages slowly. But even in its calm state, IC 1101 is not dead. It may not be forming many new stars, but it continues to evolve. Every gravitational interaction, every tidal force from a passing satellite galaxy, every minor merger with a globular cluster or dwarf galaxy adds to its story. It is a living relic, an ancient monument that still responds to its environment. Another mysterious component of IC 1101 is its population of globular clusters, dense, spherical collections of stars that orbit the galaxy like satellites. In large galaxies, these clusters can number in the thousands. IC 1101 may have more than 100,000 of them, each containing hundreds of thousands of stars. These clusters are some of the oldest structures in the universe, often predating the galaxy itself. Their orbits trace the gravitational contours of the dark matter halo, and their composition reveals the conditions of the early universe. By studying them, astronomers can peer back to the very dawn of galaxy formation. The central region of IC 1101 is also worth examining in further detail. Though we've mentioned the presence of a likely supermassive black hole, the structure of the galactic core contains several fascinating features. First, there's the core scouring phenomenon, the displacement of stars caused by binary black holes during galaxy mergers. As two black holes spiral inward, they gravitationally fling stars away from the center, hollowing out the density profile and creating a faint depression in the light curve. Observing this feature in IC 1101 is like reading the fossil record of its ancient collisions. Additionally, the dynamics of the core provide evidence for anisotropy in stellar motion, meaning that stars do not orbit randomly, but show preferred directions of motion. These orbital structures can reveal whether past mergers were head-on or off-axis, and whether the colliding galaxies were of similar size. In IC 1101, the detailed patterns of stellar orbits and velocity dispersion suggest a complex history, involving both major and minor mergers across billions of years. And still, this galaxy continues to surprise. For instance, some researchers have found evidence of a faint, extended light envelope stretching far beyond the traditionally measured limits of the galaxy. This diffuse light, known as intercluster light, is made up of stars that have been stripped from their host galaxies and now drift freely within the cluster. These stars are gravitationally bound not to any single galaxy, but to the entire cluster. Their presence in the halo of IC 1101 suggests that this galaxy has been instrumental in shaping the cluster's stellar population. This intercluster light forms an ethereal glow that fills the spaces between galaxies, barely perceptible but incredibly informative. It's like the cosmic fog of war, the remnants of ancient galactic battles where stars were torn from their homes during high-speed collisions and mergers. The fact that IC 1101 possesses such an expansive field of this diffuse light reinforces its status as a dominant gravitational force within Able 2029. It hasn't just grown by accumulating mass. It has restructured the very cluster around it, assimilating and redistributing the stars of smaller galaxies into its own extended halo. From this we gather that IC 1101 is not simply a passive structure but rather an active player in the cosmic ecosystem. It is a galactic emperor in a domain where gravitational power is the currency of influence. In the hierarchical organization of galaxy clusters, CD galaxies like IC 1101 occupy the topmost tier, central in both position and function. Their gravitational pull dictates the orbits of surrounding cluster galaxies. They may not be visually dynamic in the way spiral galaxies are, but their reach is profound and inescapable. Even the temperature and distribution of gas in Able 2029 is influenced by IC 1101. The central galaxy, due to its massive gravitational well, acts as a sink for the cluster's hot plasma. This intercluster medium, visible in X-rays, provides insight into the deeper mass distribution and offers a unique laboratory for studying the interplay between gravity and thermodynamics on a cosmic scale. Scientists use this environment to test models of galaxy evolution, particularly in high-density regions. The extreme scale and density of IC 1101 make it an ideal candidate for probing the interaction between galactic feedback, such as jets from a central black hole, and the larger cosmic web. Speaking of black holes, one of the most enigmatic aspects of IC 1101 is the potential mass of the supermassive black hole at its center. Based on correlations between the mass of a galaxy and its central black hole, researchers estimate that IC 1101's black hole could have a mass as high as 40 to 100 billion solar masses. If confirmed, this would place it among the most massive black holes ever discovered, possibly even rivaling the theoretical ultramassive black holes that may lurk in the hearts of the largest galaxies. This hypothetical black hole would not just be a gravitational monster, but a historical archive. Black holes of such mass likely grew by consuming other black holes during galaxy mergers, a process that can take millions of years and generate intense gravitational waves. As gravitational wave astronomy matures, the detection of waves from such mergers could help us reconstruct the growth history of galaxies like IC 1101, in effect turning the cosmos into a readable manuscript of its own history. But why does IC 1101 matter in the larger scheme of things? After all, it's just one galaxy among trillions. The answer lies in scale and extremes. IC 1101 serves as a boundary marker, a natural maximum in the observable range of galaxy formation. By studying what makes it so massive and enduring, we can infer the limits of galactic growth and the rules that govern structure formation in the universe. It also offers a glimpse into the future of our own galaxy. Though the Milky Way is a spiral galaxy, it is expected to merge with the Andromeda Galaxy in about 4 billion years. The resulting collision will form a new, elliptical galaxy that may resemble IC 1101, although on a much smaller scale. By observing IC 1101, astronomers are, in a way, gazing at a mirror held up to our distant future. The processes that shaped IC 1101 are the same ones that will eventually shape the fate of the local group. Additionally, IC 1101 raises critical questions about the environment in which galaxies form. Was it born in a region of space that was especially dense in matter, giving it a head start in accumulating mass? Or did it simply have an advantageous merger history? These questions are part of the larger inquiry into cosmic variance, the idea that different parts of the universe can evolve differently based on initial conditions. IC 1101 may represent a statistical outlier, a once-in-a-trillion occurrence, or it may be the natural result of long-term evolutionary processes in large clusters. Its sheer brightness also has implications for observational astronomy. IC 1101 is so large and luminous that it can be seen from enormous distances. This makes it a beacon in deep sky surveys, helping astronomers align instruments and calibrate observational data. Its presence helps map the cosmic distance ladder and contributes to our understanding of redshift, expansion, and the large-scale structure of the universe. Furthermore, IC 1101 is not just a collection of stars, gas, and dark matter. It's a community. Inside it are billions of solar systems, potentially each with their own planets, and perhaps, though we have no evidence yet, even life. While the odds of intelligent civilizations arising in such an old and evolved environment may be low, the possibility remains. The stars in IC 1101 are ancient, many formed when the universe was young. If any of those systems had the right conditions for life, and if life had the same timeline as ours, then it could be unimaginably advanced by now, or long extinct. The speculation doesn't stop there. The concept of a Kardashev Type 3 civilization, a civilization capable of harnessing the energy of an entire galaxy, often uses galaxies like IC 1101 as reference points. If any galaxy were to host such an advanced race, IC 1101, with its rich resources and vast energy output, would be a logical candidate. While this is purely theoretical, it underscores how studying extreme systems like IC 1101 stretches our imagination and our science to its limits. Even the position of IC 1101 in the cosmic web adds another layer of intrigue. Galaxy clusters like Able 2029 lie at the intersections of vast filaments of dark matter and gas, the tendrils of the cosmic web. These filaments act as highways, channeling matter toward massive nodes like IC 1101. Over billions of years, this inflow of gas and smaller galaxies fuels the growth of central giants. IC 1101 is not isolated, it is the gravitational focal point of a vast, interconnected structure that extends for hundreds of millions of light years. The cosmic web that feeds IC 1101 is not a static framework. It is a dynamic, ever-shifting network of gravitational currents and material flows. As these filaments funnel gas and dark matter toward Able 2029, they also drive the evolution of IC 1101. This steady supply of material not only contributes to the formation of new stars in its outer regions, albeit at a very slow rate given its status as a quiescent elliptical, but also increases the dark matter halo that surrounds and sustains it. This halo, largely invisible but profoundly influential, acts as a scaffold upon which the luminous components of the galaxy are built. The dark matter halo of IC 1101 is theorized to be exceptionally massive. Some models suggest it could span several million light-years across and contain hundreds of trillions of solar masses. That's more mass than all the visible matter in the entire local group of galaxies combined. This invisible structure shapes the orbits of stars within IC 1101, keeps the hot X-ray gas bound within the cluster, and guides the paths of other galaxies within Able 2029. Even though we cannot directly see this dark matter, its gravitational influence is unmistakable, and its presence is essential in explaining the dynamics of this cosmic giant. The immense mass of IC 1101 and its surrounding halo creates another fascinating effect: gravitational lensing. This phenomenon, predicted by Einstein's theory of general relativity, occurs when a massive object bends the path of light passing near it. In the case of IC 1101, its gravity can distort and magnify the light from more distant galaxies lying behind it from our perspective. This makes IC 1101 not just an object of study, but a tool for discovery, allowing astronomers to peer deeper into the universe by using it as a cosmic magnifying glass. These lensing events help researchers detect and study extremely distant, faint galaxies that would otherwise be beyond the reach of even our most powerful telescopes. In this way, IC 1101 becomes a gateway, not just a destination of inquiry, but a facilitator of further exploration. Its gravitational power extends far beyond its own boundaries, enabling the study of galaxies that lie billions of light-years farther into the cosmos. Moreover, IC 1101 challenges our understanding of the baryonic-to-dark matter ratio in galactic systems. In many galaxies, especially spirals like the Milky Way, the visible matter, stars, gas, dust, makes up a significant fraction of the total mass. But in IC 1101, the situation appears different. Its enormous dark matter halo means the visible components are a relatively small percentage of the whole. This raises intriguing questions about how galaxies form and evolve within their dark matter envelopes, and how baryonic matter can remain so centralized in such diffuse, massive structures. The age of IC 1101 stellar population also provides a window into the early universe. The stars in this galaxy are ancient. Most formed more than 10 billion years ago, not long after the first galaxies began to coalesce. Studying their composition reveals clues about the conditions in the early universe, such as the abundance of elements heavier than hydrogen and helium, known as metals, in astronomical terms. These metal ratios help scientists piece together the history of supernova explosions and star formation in the galaxy's distant past. Interestingly, the fact that IC 1101 has very little recent star formation activity doesn't mean it's completely dead. There is still evidence of low-level activity, perhaps pockets of gas where stars can still form under the right conditions, or remnants of satellite galaxies being absorbed into the larger structure. These rare events add subtle complexity to the galaxy's seemingly static appearance, and underscore the idea that even the most massive and ancient systems continue to evolve in some form. Another vital element in understanding IC 1101 lies in its interaction with the intergalactic medium. As galaxies move through the dense plasma of their host clusters, they experience a process known as ram pressure stripping, where their gas is forcibly removed by the pressure of the surrounding medium. While IC 1101, being so massive, retains much of its gas, smaller galaxies that pass nearby are often stripped of their star-forming material and gradually dissolved into IC 1101's halo. This process contributes to its size and mass while reducing the overall number of smaller galaxies in the cluster, reinforcing its dominance. Observations of the core of IC 1101 also hint at the presence of a phenomenon called core scouring. This process occurs during the merger of two galaxies with central supermassive black holes. As the black holes spiral toward each other, they gravitationally eject stars from the core region, creating a larger, more diffuse center. This may help explain why IC 1101 has a much lower stellar density in its core than would be expected based on its overall size. These ejections not only alter the structure of the galaxy but could fling stars to intergalactic space, creating rogue stars wandering alone in the void. This concept of stars being ejected into the void of intergalactic space contributes to the narrative that IC 1101 is not only vast in size but also in influence. It doesn't just absorb, it reshapes and redistributes the matter around it. It's like a cosmic sculptor, using the tools of gravity and time to mold the very landscape of the universe. The immense gravitational influence of IC 1101 also plays a role in the dynamics of the Able 2029 cluster itself. Its presence helps maintain the overall gravitational cohesion of the cluster. Without such a central mass, the individual galaxies within the cluster might drift apart over billions of years. But thanks to the gravity well provided by IC 1101 and its dark matter halo, Able 2029 remains a bound, dynamically stable system, at least on cosmological timescales. Another layer to consider is the infrared and radio emissions coming from IC 1101. Though it lacks the bright, blue light associated with new star formation, its infrared signature is significant, indicating the presence of older, cooler stars and possibly low levels of dust. Radio emissions also suggest the presence of a low-activity AGN, active galactic nucleus, possibly fueled by small amounts of matter occasionally accreting onto the central black hole. These emissions are subtle but important. They offer insight into the ongoing processes that continue to define the galaxy's character even in its advanced age. To summarize, the complexity of IC 1101 is almost impossible without acknowledging that it stands as a culmination of many universal truths. It is a monument to the quiet violence of the cosmos, a cathedral of collisions, mergers, and gravitational mastery. Its immensity doesn't just awe, it educates. It tells us about the upper bounds of galactic formation, the behavior of matter under extreme gravity, the silent tug-of-war between baryonic and dark matter, and the enduring echoes of a universe in motion. In IC 1101, we see not just a galaxy, but the fossil record of an ancient universe, a frozen storm of stars and dark matter stretching across the cosmos. It is a cosmic monolith, a silent witness to 12 billion years of history, and a puzzle whose every piece pushes our understanding of space, time, and cosmic evolution just a little bit further. The scale of IC 1101 becomes even more staggering when we try to contextualize it within the framework of the observable universe. At approximately 6 million light-years in diameter, it is more than 60 times larger than our own Milky Way. It contains an estimated 100 trillion stars, an unfathomable number when compared to the roughly 100 billion stars in our galaxy. This star count alone gives IC 1101 a level of complexity and gravitational influence that defies intuition. But it's not just about size and numbers. It's about the environment it exists in and the role it plays in shaping the region of space around it. IC 1101 resides within the Able 2029 galaxy cluster, one of the largest known collections of galaxies in the local universe. Able 2029 is not a loose, scattered collection of independent galaxies. It is tightly bound by gravity, with IC 1101 as its gravitational anchor, sitting directly at its heart. This central location is significant because it implies that IC 1101 did not just passively exist in the cluster, it likely formed alongside it, growing in tandem as the cluster assembled from smaller groups of galaxies and intergalactic gas. The process of cluster formation itself is a violent one. In the early universe, smaller proto-galaxies collided and merged to form larger ones, and clusters like Able 2029 were born from the gravitational aggregation of these early systems. Over time, these galaxies fell toward the center, drawn by the gravitational pull of the densest regions. IC 1101, situated at the center of this ancient storm, acted as a galactic sponge, absorbing countless smaller galaxies, increasing in mass and volume with each merger. These mergers are not simple additions. When two galaxies combine, their stars may pass through each other with minimal direct collision due to the vast empty spaces between them, but their mutual gravitational fields interact intensely. These interactions distort their shapes, funnel gas toward the center, and trigger bursts of star formation. In the case of IC 1101, these bursts likely occurred in the distant past, billions of years ago, when the galaxy was still in its formative phase. Today, IC 1101 shows few signs of ongoing star formation. Its stellar population is dominated by old, red, metal-rich stars, the remnants of ancient starbursts that occurred when the universe was young. This population gives the galaxy its golden yellow hue, a visual indicator of its age and relative inactivity. However, this doesn't mean the galaxy is static. It continues to grow in mass through a process called galactic cannibalism, absorbing smaller galaxies that venture too close, pulling them in with its immense gravitational pull and assimilating their stars and dark matter into its own structure. This slow, steady growth has shaped IC 1101 into a nearly perfect elliptical galaxy. Unlike spiral galaxies, which have well-defined arms and central disks, elliptical galaxies like IC 1101 lack clear structure. They are more like cosmic clouds of stars, dense in the center and gradually thinning out toward the edges. In IC 1101's case, these edges stretch far beyond what we would consider normal for a galaxy. In fact, the outer halo of IC 1101 may blur into the intergalactic medium of the cluster itself, making it difficult to determine where the galaxy truly ends and the cluster begins. From an observational standpoint, IC 1101 poses significant challenges. Its distance, over 1 billion light-years from Earth, means that even with the most powerful telescopes, we can only observe it as it was 1 billion years ago. Every image we capture is a snapshot of the distant past, a ghost image of a galaxy that may have evolved considerably since that light first left its stars. This time lag, while limiting, also provides a kind of cosmic archaeology, allowing scientists to study how galaxies and clusters looked long ago, and how they may have changed over the eons. Despite the distance, IC 1101 is bright enough to be studied in detail, thanks to its immense size and mass. Its core, in particular, reveals a great deal about its history. Spectroscopic analysis of the light coming from its central region shows a lack of young, hot stars and an abundance of older, cooler ones. This supports the idea that the galaxy's most active periods of star formation are long behind it, and that it has entered a mature, stable phase in its life cycle. Yet even in this maturity, IC 1101 continues to command attention. Its supermassive black hole, suspected to be one of the largest ever discovered, lies at the center of its vast mass. These behemoths, millions or even billions of times the mass of the Sun, are common in massive galaxies, but the one in IC 1101 could be in a league of its own. Some estimates suggest its mass could be tens of billions of solar masses, rivaling or exceeding that of the black hole in TON 618, another cosmic titan. Such an object would have a gravitational influence stretching over light years, warping the space around it, and affecting the orbits of stars even far from the core. Black holes of this magnitude are thought to grow through two main processes: the accretion of gas and the merging of other black holes. In IC 1101, both processes were likely at work. As the galaxy absorbed others, their central black holes would have sunk toward the center, eventually merging into a single, larger object. These mergers are cataclysmic, releasing vast amounts of gravitational waves, ripples in the fabric of spacetime. Though we cannot detect such waves from that distance today, future advancements in gravitational wave astronomy may one day allow us to hear the echoes of those ancient collisions. The history of IC 1101 is also written in the distribution of its globular clusters, dense groups of old stars that orbit the galaxy like tiny satellites. These clusters act as tracers, helping astronomers map the galaxy's gravitational field and infer its dark matter distribution. The number and distribution of globular clusters around IC 1101 suggest a tumultuous past, one shaped by frequent mergers and the gradual accretion of smaller systems. In terms of gas content, IC 1101 is relatively poor compared to more active galaxies. The hot gas that does exist tends to remain in the cluster environment, held in place by the collective gravity of the entire Able 2029 system. This gas emits X-rays, which can be detected by space-based observatories. These X-ray emissions help researchers understand the temperature and density of the intracluster medium and offer clues about the history of energy input from supernovae, AGNs, and other high-energy processes. What makes IC 1101 particularly fascinating is that despite its sheer scale, it may not be unique in the universe. While it is currently the largest known galaxy in terms of physical diameter and stellar mass, simulations of cosmic structure formation suggest that even larger galaxies may exist, hidden in the vast reaches of the cosmos, yet to be discovered. These hypothetical giants would be the result of similar processes: mergers, accretion, and the gravitational settling of matter in the densest regions of the universe. If and when we discover such galaxies, IC 1101 will still stand as the standard by which we measure them, a towering benchmark in our quest to understand the cosmos. IC 1101 invites us to consider a universe that operates on scales almost impossible to grasp. It is not merely a collection of stars, it is a monument to the passage of cosmic time, a survivor of the universe's most dramatic events, and a key to unlocking the mysteries of galactic evolution. Its story is not just one of growth, but of transformation, from a simple, young galaxy in the early universe to a colossal structure that shapes and defines an entire cluster. The sheer longevity of IC 1101 is another aspect that sets it apart as an extraordinary cosmic entity. It has existed for billions of years, possibly over 12 billion, surviving the turbulent periods of the early universe, the peak of star formation across the cosmos, and the successive gravitational chaos of galaxy mergers. As a result, IC 1101 is not only ancient but also evolved. It has passed through every known stage of galactic development, from proto-galactic cloud to merger-dominated elliptical titan. Its light, taking over 1 billion years to reach us, carries with it the fossilized record of a universe far younger than the one we now inhabit. To consider the intricacies of such a structure is to attempt to understand a puzzle assembled over eons, where each piece is shaped by cosmic forces of unimaginable magnitude. One of the more enigmatic aspects of IC 1101 is its outer halo, the vast, diffuse region that extends millions of light-years from the galactic core. While we often think of galaxies as having defined edges, IC 1101 challenges this assumption. Its faint halo is so extended that it blurs the line between where the galaxy ends and the intercluster space of Able 2029 begins. This sprawling envelope is populated by stars, stellar remnants, globular clusters, and dark matter, all remnants of the many galaxies that IC 1101 has consumed over the ages. This peripheral region is important for several reasons. First, it serves as a repository for stars stripped from infalling galaxies. As these smaller systems spiral into IC 1101, gravitational tidal forces pull them apart, scattering their stars into the outer halo. Second, it houses a significant amount of dark matter, the invisible scaffolding that holds the galaxy together. While dark matter cannot be seen directly, its gravitational influence can be detected through the motion of stars and globular clusters in the galaxy's outskirts. These motions reveal a mass far greater than can be accounted for by visible matter alone, confirming the presence of a vast, dark component that plays a central role in the galaxy's structure and stability. Moreover, the shape and brightness profile of IC 1101's outer halo provide clues to its merger history. A smooth, gradually declining brightness suggests a long history of gradual accretion, while irregularities or asymmetries may point to recent galactic cannibalism events. By studying these light profiles in detail, astronomers can reconstruct the galaxy's growth over time, much like a geologist reading layers of sedimentary rock to understand Earth's history. One of the most striking implications of IC 1101's existence is its challenge to current models of galaxy formation. According to the standard cosmological model, the lambda cold dark matter model, large galaxies form hierarchically, starting small and growing larger through mergers. IC 1101, however, seems to be an extreme outlier in terms of how massive and extended a galaxy can become. Its very existence suggests that in the densest environments, like the center of a massive cluster, galaxies can grow far beyond what is typical through a continuous chain of mergers and accretions. This realization is forcing scientists to refine their simulations to better account for the growth of such giants, and to reconsider the upper limits of galaxy formation. Adding to this complexity is the dynamic interplay between IC 1101 and the superheated intracluster medium, ICM, that fills Able 2029. This medium consists primarily of ionized hydrogen at temperatures reaching tens of millions of degrees Kelvin. Although it is incredibly diffuse, it emits strongly in X-rays and can influence galactic evolution in subtle ways. For instance, When smaller galaxies move through this hot medium, they experience ram pressure stripping, a process by which their gas is pushed out by the pressure of the ICM, halting star formation and contributing to the overall quenching of the galaxy. In the case of IC 1101, its central location within the cluster means it bathes in this hot gas, which may have helped shut down star formation by stripping away the last reservoirs of cold gas. Furthermore, the activity of the galaxy's central black hole, referred to as an active galactic nucleus, AGN, when it is feeding, could also contribute to this quenching. AGNs can produce powerful jets of radiation and high-energy particles that heat the surrounding gas and prevent it from cooling and condensing into new stars. Though IC 1101's AGN appears relatively dormant today, it likely went through a highly active phase in the past. The energetic feedback from such a phase would have affected not only the galaxy's internal structure but also the entire cluster environment, injecting energy into the ICM and regulating the thermal balance of Able 2029. The mechanics of such feedback are still an area of active research, but one thing is clear: IC 1101 is not a passive resident of its cluster. It has shaped its surroundings as much as it has been shaped by them. This reciprocal relationship between galaxy and environment is a cornerstone of modern astrophysics and helps us understand the cosmic web, the vast, filamentary structure of the universe in which galaxies, clusters, and superclusters are embedded. IC 1101, as a brightest cluster galaxy, BCG, is a vivid testament to this interaction. BCGs are typically located at the gravitational center of a cluster, and are usually among the most massive and luminous galaxies in the universe. They are thought to form through the combination of multiple galaxies at the center of a cluster's gravitational well. In this respect, IC 1101 is the archetype of a BCG, gargantuan, luminous, and ancient. Yet, it exceeds even the usual parameters of BCGs, earning its place as a cosmic anomaly. Because of these features, IC 1101 is not just a point of interest for astronomers, but also a calibration tool for observational cosmology. By studying such extreme galaxies, researchers can test the limits of their theories. If simulations fail to produce a galaxy like IC 1101 under realistic conditions, it suggests that there are gaps in our understanding of galaxy evolution, dark matter behavior, or the role of feedback mechanisms. Thus, IC 1101 is not merely an object of curiosity, it is a lens through which we examine the validity of the physical laws that govern the universe. From a philosophical standpoint, IC 1101 also invites reflection on our place in the cosmos. Its sheer scale dwarfs the Milky Way and humbles our understanding of the universe. While we often think of our galaxy as vast and complex, and it is, IC 1101 represents an entirely different level of grandeur. It is a realm of billions of solar systems, an ocean of starlight so vast that light itself takes millions of years to cross its breadth. It reminds us that the universe is not just large, but layered with levels of scale that challenge human comprehension. Even the notion of largest galaxy becomes somewhat nebulous in light of IC 1101. Galaxies are not perfectly defined objects, they have fuzzy boundaries, ongoing interactions with their environments, and long histories of transformation. What we observe today is just one stage in a process that spans billions of years. In that sense, IC 1101 is a snapshot in a cosmic film, a still image in a dynamic process that continues to unfold. This realization deepens when we consider the future of IC 1101. Over the next tens of billions of years, if the universe continues expanding indefinitely, it may continue to absorb more galaxies as they fall inward toward the cluster center. Eventually, however, the accelerated expansion of the universe driven by dark energy will isolate IC 1101, cutting it off from the rest of the cosmic web. In this far future, it may stand alone in a darkening universe, its light stretching redder and dimmer as space itself expands. In this lonely state, it will still carry within it the memory of a universe once teeming with light and structure. In essence, IC 1101 is a bridge between the past and the future, between small and large scale, and between observation and theory. It is a cosmic archive of galactic history and a beacon for future exploration. Every photon we receive from it is a message from deep time, and every detail we uncover adds a new layer to our understanding of what galaxies are, how they grow, and where our universe is headed. The vastness of IC 1101 also provides an essential platform for studying galaxy mergers, one of the key processes behind its extraordinary size and structure. Galactic mergers are pivotal moments in the lives of galaxies, often resulting in massive growth or transformation. When galaxies collide, their stellar populations mix, and their gas clouds interact, potentially igniting bursts of star formation, creating new cosmic structures, and triggering the creation of supermassive black holes at their centers. In the case of IC 1101, its current size and structure are likely the result of several such mergers, spanning billions of years. In galaxy clusters like Able 2029, galaxies often move toward the center, pulled by gravity. Over time, this results in the merging of smaller galaxies into larger ones. IC 1101, located at the center of the Able 2029 cluster, has been the recipient of many such mergers. These processes have not only contributed to the galaxy's immense size but also have a profound impact on the evolution of its central black hole, star formation, and the surrounding intercluster medium. This merging process makes IC 1101 an excellent subject for studying the broader dynamics of galaxy cluster evolution and the role of galaxy interactions in shaping their final forms. Astronomers speculate that the ultimate fate of IC 1101 might be influenced by its location at the center of Able 2029. Galaxies in such positions often play a dominant role in the evolution of their clusters. As we mentioned earlier, IC 1101's supermassive black hole is likely to be an active player in this cosmic drama. When galaxies merge, their black holes eventually spiral towards each other, and can coalesce to form even more massive black holes. The process releases enormous amounts of energy, which can have a profound impact on the surrounding environment, affecting the galaxy's star formation and gas dynamics. The feedback loops between IC 1101's black hole and its environment may be responsible for regulating the amount of gas available for future star formation, thus contributing to the galaxy's eventual quiescence. However, IC 1101's future is not as certain as its past. As the universe continues to expand, the ability of galaxy clusters to grow through mergers and accretions may decrease. The accelerating expansion of the universe is causing galaxies and other clusters to move away from one another at an ever-increasing rate. This cosmic isolation will eventually reach a point where clusters will no longer interact, and galaxies like IC 1101 will no longer experience new mergers. While IC 1101 may eventually cease its growth, the legacy of its massive structure and its dark matter halo will continue to persist for eons to come. An intriguing aspect of IC 1101's immense size is the question of whether it will continue to grow or eventually reach a point where it cannot absorb any more material. As mentioned earlier, the vast outer halo of IC 1101 contains stars and gas stripped from smaller galaxies that have merged with it over time. But eventually, the galaxy may run out of smaller galaxies to consume. Will it then enter a phase of stagnation, or will it continue to evolve in other ways? This remains an open question, as IC 1101's future is influenced not only by internal processes, but also by the changing dynamics of the universe itself. At present, one of the biggest mysteries about IC 1101 concerns the nature of its dark matter component. Like most large galaxies, IC 1101 is surrounded by a dark matter halo, which accounts for much of its mass. Dark matter is one of the universe's greatest mysteries, as it does not emit, absorb, or reflect light, making it nearly invisible to traditional observational tools. However, astronomers can detect its presence by observing the gravitational effects it has on visible matter. In the case of IC 1101, the galaxy's outer halo exhibits the telltale signs of dark matter's influence. Its stars move much faster than would be expected if only visible matter were present. This dark matter halo is not merely a passive bystander in the evolution of IC 1101. It is an active participant, shaping the galaxy's structure, mass distribution, and even the way it interacts with its environment. Some researchers hypothesize that dark matter may have influenced the way IC 1101 stellar population is distributed, potentially contributing to the galaxy's remarkable size and the large number of stars in its outer regions. Understanding how dark matter interacts with normal matter in such extreme environments could yield important insights into the nature of dark matter itself. The study of IC 1101 also raises important questions about the role of supermassive black holes in the evolution of galaxies. At the center of IC 1101 lies a supermassive black hole that weighs in at an astonishing mass, billions of times that of our Sun. Like the galaxy itself, this black hole is a cosmic heavyweight. The properties and behavior of such a massive black hole have important implications for our understanding of the relationship between a galaxy and its central black hole. Is the size of a galaxy determined in part by the mass of its central black hole, or is it the other way around? Can the feedback from a supermassive black hole actually shape the evolution of a galaxy? These are critical questions that astronomers are still working to answer, and IC 1101 provides a prime candidate for answering them. The supermassive black hole at the heart of IC 1101 is currently thought to be relatively inactive compared to other more energetic black holes found in active galactic nuclei, AGN. However, this does not mean that it has always been this way. Over the course of the galaxy's history, the central black hole may have gone through phases of violent activity, ejecting powerful jets of high-energy particles into space. These jets could have had profound effects on the surrounding gas and star formation, potentially contributing to the galaxy's current lack of star formation in its central regions. Understanding how these jets form and how they influence the galaxy's evolution is another area of active research. One of the most compelling aspects of IC 1101 is its connection to the broader structure of the universe. As a member of the Able 2029 galaxy cluster, IC 1101 offers a glimpse into the dynamics of galaxy clusters, the largest gravitationally bound structures in the universe. These clusters contain hundreds or even thousands of galaxies, bound together by gravity, and they play a key role in the large-scale structure of the universe. The study of these clusters, and the galaxies they contain, helps scientists understand how galaxies interact with each other, and how clusters themselves evolve over time. IC 1101, as the dominant galaxy in Able 2029, is a central player in these interactions and an essential piece of the puzzle that is galaxy cluster evolution. In addition to its sheer size, IC 1101 serves as a unique test case for our understanding of galaxy evolution and formation. Because of its immense size and age, IC 1101 has experienced many of the same processes that affect all galaxies, but on an exaggerated scale. By studying IC 1101, astronomers can test their theories of galaxy formation and evolution in a laboratory that stretches the limits of what is possible. It's a living example of the kinds of galaxies that were likely more common in the early universe, and its study may reveal insights into how galaxies like the Milky Way, and even larger galaxies, might evolve in the future. The future of IC 1101, like the rest of the universe, is subject to the forces of cosmic evolution. As the universe continues to expand and galaxies grow further apart, the role of massive galaxies like IC 1101 may change. Will it continue to be the dominant force in Able 2029, or will the expansion of the universe lead to its isolation, leaving it as a relic of a bygone era? Only time will tell. Despite the questions still surrounding it, IC 1101 remains one of the most fascinating objects in the universe. Its enormity, its history, and its connection to the evolution of galaxy clusters make it an essential subject of study. As astronomers continue to learn more about this cosmic giant, they not only uncover the secrets of IC 1101 itself but also gain a deeper understanding of the processes that govern the formation and evolution of galaxies across the universe. As we look deeper into the cosmos, beyond our own galaxy and even the local group, we are reminded of the vast scale of the universe. IC 1101, with its sprawling structure, provides a stark contrast to our relatively modest Milky Way and serves as a reminder that the universe is full of surprises, each discovery leading to more questions and more mysteries to explore. As we continue our journey of exploration, IC 1101 stands as a symbol of both the limits of human understanding and the infinite possibilities that await discovery. IC 1101's place in the cosmos as an extraordinary outlier reminds us of the hidden wonders that exist beyond the limits of our immediate comprehension. With its immense size, deep-rooted history, and central position within the able 2029 galaxy cluster, it acts as a beacon for scientific inquiry, a critical piece of the puzzle in understanding galaxy formation, evolution, and the fundamental forces that govern the universe. But despite all the revelations about its structure, interactions, and history, IC 1101 also underscores how much we still don't know. The further we probe, the more fascinating and complex the universe reveals itself to be. IC 1101, in this sense, is not just an astronomical object, but a cosmic laboratory, offering insights that push the boundaries of human knowledge. A key aspect of understanding IC 1101, and indeed any galaxy, is exploring the relationship between the galaxy's visible matter, the stars, gas, and dust, and its invisible counterpart, dark matter. While we know that galaxies like IC 1101 are surrounded by a vast dark matter halo, the true nature of dark matter remains elusive. Dark matter makes up approximately 85% of the mass of the universe, yet it doesn't interact with electromagnetic forces, making it invisible to conventional telescopes. It is detectable only through its gravitational effects. This paradoxical nature makes dark matter both elusive and enigmatic. IC 1101's dark matter halo is particularly interesting because it represents a more massive version of the halos around typical galaxies, a feature that could offer clues about the fundamental nature of dark matter. As astronomers look deeper into the characteristics of dark matter, galaxies like IC 1101 could provide valuable clues. For example, the unusually extended dark matter halo of IC 1101 could suggest new theories about the nature of dark matter and how it behaves in such extreme environments. If dark matter is crucial to the formation and growth of galaxies, its distribution in massive galaxies like IC 1101 could help us refine our models of galaxy evolution and the physics that govern it. The way that IC 1101's dark matter halo interacts with the surrounding gas and visible matter is essential for understanding not just this one galaxy, but galaxies in general. As research continues, we may uncover more about the mysterious substance that makes up the bulk of the universe's mass. Another fascinating aspect of IC 1101 lies in its role within the broader context of galaxy clusters. These massive collections of galaxies, bound together by gravity, serve as laboratories for studying the interplay between galaxies and the intergalactic medium. In the case of IC 1101, located at the center of the able 2029 cluster, it plays a dominant role in shaping the dynamics of the entire cluster. Galaxy clusters, like able 2029, act as cosmic factories for the creation and destruction of galaxies. Galaxies within clusters interact, collide, and merge, and these interactions can lead to the growth of supermassive black holes, the creation of vast new stellar populations, and the disruption of the gas in the cluster. The gas, which is mostly composed of ionized hydrogen, is heated to millions of degrees as it is compressed by the gravitational pull of the galaxies. This heated gas can then be observed by astronomers using X-ray telescopes, providing critical insight into the processes happening in these clusters. At the heart of these interactions is IC 1101, the gravitational giant that dominates its cluster. The galaxy's sheer size and mass influence the movement of other galaxies within able 2029, and the forces it exerts play a significant role in the behavior of the cluster as a whole. It is believed that IC 1101's gravitational pull has helped shape the distribution of galaxies within the cluster, and its supermassive black hole may also be contributing to the dynamics of the intergalactic gas. By studying IC 1101 and its role in able 2029, astronomers can learn more about how galaxy clusters evolve and how individual galaxies interact with the broader cosmic web. Another intriguing question surrounding IC 1101 involves its central supermassive black hole. Most galaxies, including our own Milky Way, host a supermassive black hole at their centers. These black holes are thought to play a key role in the evolution of galaxies, influencing star formation, galaxy dynamics, and even the behavior of gas and dust. However, the precise relationship between galaxies and their central black holes is still not fully understood. In the case of IC 1101, the black hole is exceptionally massive, and while it is not currently active in the sense of emitting powerful radiation like those found in active galactic nuclei, AGN, it may have experienced periods of intense activity in the past. The history of IC 1101's central black hole is a subject of much interest. Scientists believe that at some point in its history, the black hole may have experienced a feeding frenzy, accreting large amounts of material from its surroundings. This process, which is known as active galactic nucleus, AGN, activity, can result in the release of enormous amounts of energy. IC 1101's black hole could have once been an AGN, expelling jets of energetic particles and influencing the surrounding galaxy. Over time, however, as the material around the black hole was consumed or stripped away, the black hole may have entered a more dormant phase. While it may not currently be as active as other supermassive black holes in the universe, its sheer size and mass are a testament to the power it once held. The question of how black holes interact with their host galaxies is a central one in modern astrophysics. Do black holes shape the evolution of galaxies? Or do galaxies shape the growth of black holes? Some researchers argue that black holes regulate the rate of star formation in their galaxies by heating or expelling gas, preventing it from collapsing into new stars. This process, known as feedback, is a critical mechanism in the evolution of galaxies. In the case of IC 1101, the relationship between its massive black hole and the galaxy's lack of active star formation may provide insights into how such feedback mechanisms work. Does the central black hole of IC 1101 play a role in quenching star formation, or is the galaxy's old age and lack of gas the primary reason for its quiescence? One of the most puzzling aspects of IC 1101 is its age and lack of star formation. Despite its enormous size, the galaxy is not actively forming new stars. Most galaxies, including the Milky Way, continue to form stars from the gas available to them, but IC 1101 seems to have exhausted its supply of gas or perhaps never had enough to sustain ongoing star formation. This is a significant departure from the norm for massive galaxies, and understanding why IC 1101 has ceased star formation is crucial for understanding the life cycle of galaxies in general. It is possible that IC 1101's large black hole played a role in shutting down star formation, either by expelling gas from the galaxy or by heating the gas to the point where it could no longer collapse to form stars. Alternatively, it could simply be that the galaxy has reached the end of its evolutionary life cycle, with no new gas available to fuel the creation of new stars. The end stages of a galaxy's life are an area of growing interest in astrophysics. While galaxies like IC 1101 may seem dormant, they are still evolving in their own way. Some scientists have suggested that galaxies like IC 1101, which are devoid of new star formation, could eventually fade into oblivion, becoming what is known as a red and dead galaxy. These galaxies are characterized by their red color, which results from the aging of their stars, and their lack of any new stars being born. However, it is also possible that such galaxies could undergo a period of rejuvenation if they are able to accrete new gas or experience a merger with another galaxy. Ultimately, the future of IC 1101 may be shaped by the same forces that have shaped its past: galactic interactions and the expansion of the universe. As the universe continues to expand, the Able 2029 galaxy cluster may eventually experience a slowdown in its ability to accrete new galaxies. This means that galaxies like IC 1101, which have already grown to massive sizes, may not experience further mergers or significant growth. Instead, they may enter a period of stagnation, where they will slowly fade into the cosmic background, becoming less and less active over time. Whether IC 1101 will continue to grow, or whether it will enter a period of dormancy, is something that will only be answered by time and further study. The study of IC 1101, in all its grandeur and complexity, is a testament to the power of exploration and discovery. It challenges our understanding of the universe, pushing the boundaries of what we thought was possible in terms of size, evolution, and cosmic history. It is a reminder that, in the vast expanse of the universe, there are still mysteries waiting to be uncovered, and the pursuit of knowledge is a never-ending journey. IC 1101, with all its wonders, will continue to be a focal point of scientific inquiry for years to come, offering new insights into the nature of galaxies, dark matter, black holes, and the fundamental forces that govern the cosmos. The presence of IC 1101 in our understanding of the universe is a critical one. Its sheer size and complexity spark a deeper fascination with how galaxies evolve over time. It's a reminder that our local perspective, limited to our Milky Way, represents only a small fraction of what the universe holds. Galaxies like IC 1101 act as windows into the distant past and future of galaxy formation. By studying these behemoths, we can begin to unravel the many complex threads of cosmic evolution. As we continue to explore these massive galaxies, it's crucial to address the broader implications of their discovery. IC 1101 is more than just a galaxy in a distant cluster. It's a living testament to the cosmic forces that shape the very fabric of the universe. The formation and growth of galaxies are processes that stretch over billions of years, and the history embedded in each galaxy provides a crucial piece of the puzzle of how our own Milky Way might evolve. One of the most interesting and still poorly understood aspects of IC 1101 structure is the interplay between its stars and the dark matter that surrounds it. Dark matter, though invisible and undetectable by traditional means, constitutes the vast majority of the mass in galaxies like IC 1101. It's believed to exist in large, diffuse halos that extend far beyond the visible limits of the galaxy. These dark matter halos influence the galaxy's gravitational structure, providing the necessary mass to hold the galaxy together. In the case of IC 1101, the dark matter halo is especially important because of the galaxy's extreme size. Given the enormity of IC 1101, the galaxy's halo likely extends far beyond what we would consider the typical boundary of a galaxy. This extended dark matter halo plays a significant role in stabilizing the galaxy and its surrounding gas, allowing the galaxy to maintain its immense size. It also influences the rate of star formation and the dynamics of gas inflows and outflows. While the visible stars within IC 1101 provide a glimpse into the galaxy's past, the invisible dark matter reveals a far deeper story about the forces that shape the universe. IC 1101's central supermassive black hole is another area where significant mysteries remain. The size of this black hole and its apparent lack of active accretion, a feature often observed in supermassive black holes at the centers of other galaxies, raises many questions. How does a galaxy like IC 1101 form such a large black hole? And why doesn't it continue to feed on its surrounding material in the same way other active galactic nuclei do? The absence of active accretion may also provide insights into the long-term evolution of black holes and massive galaxies. In many ways, supermassive black holes are central to the overall health of their host galaxies. The energy they release, both through radiation and powerful jets, can influence star formation rates and the surrounding gas dynamics. The apparent inactivity of IC 1101's black hole suggests that the galaxy has passed through an active phase and is now in a more dormant period. But this doesn't mean the black hole is inactive. It's likely still emitting radiation, albeit at much lower levels, and its presence continues to shape the galaxy in subtle ways. Future studies of IC 1101's black hole could shed light on how these cosmic giants evolve and how they interact with their host galaxies over time. The fate of IC 1101, along with the fate of other galaxies in the Able 2029 cluster, is another area of deep intrigue. Galaxy clusters like Able 2029 are dynamic, ever-changing environments. Galaxies within these clusters are constantly interacting with one another through gravitational forces. Collisions between galaxies, the stripping of gas, and the merging of galaxies are all common events in these crowded environments. In some cases, galaxies are completely stripped of their gas during these interactions, which can halt star formation and lead to the eventual death of the galaxy. IC 1101's immense size and central position make it a key player in the dynamics of Able 2029, and its future will likely be shaped by the interactions with its neighbors. Interestingly, IC 1101 is located at the heart of the cluster, and it has likely experienced several interactions with other galaxies throughout its long history. These interactions may have played a role in shaping its current structure, including the apparent cessation of star formation. The galaxy's size may also indicate that it has been the product of multiple mergers over time. In fact, massive galaxies like IC 1101 are thought to grow primarily through the merging of smaller galaxies, a process that would explain its incredible size and structure. While IC 1101 may have slowed down in its growth, it may still be undergoing gradual evolution as it continues to interact with the galaxies in Able 2029. The mysteries of galaxy mergers are also worth exploring. When two galaxies merge, they can create a burst of star formation known as a starburst. This burst of activity occurs when the gas from both galaxies is compressed, triggering the formation of new stars. Over time, however, the gas supply is often exhausted, leading to a lull in star formation. This is a common fate for many galaxies, and it may explain why IC 1101 has ceased forming stars. The lack of new gas entering the galaxy, combined with the potential heating effects from its supermassive black hole, may have contributed to its current quiescent state. In the grander context of galaxy evolution, the process of merging and evolving is a critical component of how large galaxies like IC 1101 form. Over billions of years, galaxies collide, merge, and grow, leading to the creation of the massive, elliptical galaxies we observe today. IC 1101's incredible size suggests that it has experienced multiple mergers throughout its lifetime, which could explain why it has become the behemoth that it is today. The concept of galaxy mergers also extends to the future. In a few billion years, the Milky Way is predicted to collide with the Andromeda Galaxy. This impending collision will lead to a merger, ultimately resulting in the formation of a new, larger galaxy. This process of galaxy evolution is a universal phenomenon, and galaxies like IC 1101 provide a glimpse into what our own galaxy's future might look like. While IC 1101 is much older and more evolved than our Milky Way, it represents a future we are yet to experience, a future where galactic interactions are at the heart of cosmic evolution. IC 1101 also presents a unique opportunity for astronomers to study the conditions in the early universe. As one of the largest galaxies ever discovered, it offers a glimpse into what galaxies may have looked like during the earlier stages of the universe's evolution. By studying IC 1101, scientists can gain insights into the processes that shaped early galaxy formation and the cosmic structures that followed. This is crucial for understanding how the universe has evolved over time and how galaxies like our own will continue to evolve. The study of galaxies like IC 1101 also deepens our understanding of the large-scale structure of the universe. Galaxies are not isolated entities but are part of a vast cosmic web, with vast regions of empty space separating them. These regions, known as voids, contain very few galaxies, while the spaces between galaxy clusters are filled with a diffuse gas known as the intergalactic medium. The interaction between galaxies, their dark matter halos, and the intergalactic medium helps to shape the universe's structure on the largest scales. IC 1101's position at the center of the Able 2029 cluster makes it an ideal candidate for studying these interactions. By understanding how galaxies like IC 1101 fit into the larger cosmic web, astronomers can better understand the universe's overall structure and evolution. IC 1101 is more than just an awe-inspiring astronomical object. It represents a key piece of the cosmic puzzle. Its size, age, and location within the Able 2029 galaxy cluster provide valuable insights into galaxy formation, dark matter, supermassive black holes, and the evolution of the universe. While much remains to be discovered about this enormous galaxy, each new observation brings us closer to understanding the fundamental forces that shape the cosmos. As we continue to explore the mysteries of IC 1101, we are reminded of the vastness of the universe and the incredible complexity that lies beyond our immediate grasp. The story of IC 1101 is one of cosmic wonder, scientific discovery, and the endless pursuit of knowledge. It is a reminder that, even in the farthest reaches of the universe, there is still much to uncover. IC 1101's immense size is not the only feature that distinguishes it from other galaxies. Its age and the insights it offers about the future of galaxies make it a particularly intriguing object of study. The cosmic timeline that has brought IC 1101 to its current state is something that astronomers are piecing together, using both observational data and theoretical models. These models are often based on the standard cosmological model, which includes the expansion of the universe, the formation of galaxies, and the eventual merger of cosmic structures. IC 1101, sitting at the heart of the Able 2029 cluster, is a relic of this long cosmic journey, providing valuable clues about how galaxies form, evolve, and eventually reach their ultimate fate. When studying IC 1101, astronomers face the challenge of understanding both its history and its future. The galaxy's past is written in the stars, in the way it has accumulated mass and formed its structure. Its future is tied to the behavior of its supermassive black hole and the continuing evolution of its environment within the galaxy cluster. As galaxies like IC 1101 merge and interact, they can experience profound changes in their star formation rates, their dynamics, and the distribution of matter within them. These interactions are critical to understanding how galaxies evolve over time, and IC 1101 offers an opportunity to study a galaxy that has already undergone many of these processes. The way galaxies like IC 1101 form and evolve is deeply connected to their environment. Galaxy clusters like Able 2029 are incredibly dense regions of space, containing hundreds or even thousands of galaxies. In these clusters, galaxies are not isolated. Instead, they interact with one another through gravitational forces. This can lead to a variety of outcomes, from the gradual merging of galaxies to the stripping of gas and stars from the galaxies at the cluster's center. IC 1101's massive size suggests that it has been shaped by many such interactions over billions of years. By studying how IC 1101 interacts with the other galaxies in Able 2029, astronomers can learn more about how galaxy clusters influence the growth and evolution of individual galaxies. At the heart of these interactions lies the central supermassive black hole. Supermassive black holes are thought to reside at the centers of most galaxies, playing a key role in their formation and evolution. IC 1101's black hole is particularly interesting because it appears to be relatively inactive, which stands in stark contrast to the active supermassive black holes observed in many other large galaxies. This inactivity raises several questions. How did IC 1101's black hole grow to such massive proportions? Why does it appear to be dormant today, when other black holes are constantly feeding on surrounding material? Understanding the evolution of IC 1101's black hole could provide vital insights into the relationship between supermassive black holes and the galaxies that host them. In many ways, the activity of a galaxy's central black hole reflects the overall health and growth of the galaxy itself. Active black holes emit powerful radiation, which can have significant effects on their host galaxies. This radiation can heat the surrounding gas, preventing it from collapsing into new stars and thus quenching star formation. The lack of such activity in IC 1101 suggests that it may have entered a quiet phase after a period of intense growth, a phase that many massive galaxies eventually experience. By studying IC 1101's black hole, astronomers hope to understand the long-term evolution of these cosmic giants and how they impact the galaxies that house them. The interactions between galaxies and their supermassive black holes are also tied to the broader phenomenon of galaxy mergers. As galaxies collide and merge, their black holes may eventually coalesce, forming an even larger supermassive black hole. This process is thought to be a major driver of the growth of black holes in the universe. IC 1101's size and position at the center of its cluster suggests that it has likely experienced numerous mergers in the past, each contributing to the growth of its supermassive black hole. These mergers may have played a role in the galaxy's current structure, including its enormous size and relatively low rate of star formation. Interestingly, galaxy mergers are also a key factor in the formation of elliptical galaxies. IC 1101 is classified as an elliptical galaxy, a type that typically forms through the merging of smaller galaxies. Elliptical galaxies are often much larger and more massive than their spiral counterparts, and they tend to have older stellar populations with little to no ongoing star formation. The process of merging and accreting new stars and gas likely led to the formation of IC 1101's enormous size, and it may continue to influence the galaxy's evolution in the future. By studying IC 1101, astronomers can gain insights into how elliptical galaxies form and evolve, and how mergers play a key role in their growth. As we consider the role of IC 1101 in the larger cosmic landscape, it's important to remember that this galaxy is not an isolated anomaly but part of a much larger structure, the universe itself. IC 1101's position at the center of the Able 2029 galaxy cluster places it within a vast cosmic web, where galaxies are interconnected by gravity. This web of galaxies, clusters, and voids forms the large-scale structure of the universe, a structure that is still not fully understood. By studying galaxies like IC 1101, astronomers can learn more about how galaxies fit into this larger structure and how they evolve over time. The universe is a dynamic place, and galaxies like IC 1101 are not static objects. They evolve and change over billions of years, growing, merging, and sometimes dying in spectacular ways. The study of IC 1101 offers a unique window into the past and future of galaxy formation. Its massive size, central location in a galaxy cluster, and potential for further evolution make it a fascinating object of study, one that can teach us more about how galaxies form, grow, and eventually fade away. As we continue to observe IC 1101 and similar galaxies, we gain a deeper understanding of the forces that shape the universe and the incredible diversity of objects that exist within it. IC 1101 is a prime example of the complex and fascinating world of galaxy formation and evolution. From its massive size and position at the heart of its galaxy cluster to the mysteries of its supermassive black hole and the ongoing dynamics of its environment, IC 1101 offers a wealth of scientific questions waiting to be explored. As we continue to explore the universe and study the galaxies within it, objects like IC 1101 will continue to challenge our understanding of the cosmos, pushing the boundaries of what we know and revealing new insights into the nature of the universe itself. IC 1101 is a reminder of the vastness of space and the immense scale on which the universe operates. The fact that a single galaxy can span more than 6 million light-years is a humbling thought. It puts into perspective the incredibly small and fleeting nature of our own existence. Yet, it also reinforces the notion that our understanding of the universe is constantly evolving. Every new discovery, every new observation, brings us closer to answering the fundamental questions about the cosmos. IC 1101 is just one of many galaxies in the universe, but its unique characteristics make it a key to understanding the larger picture of cosmic evolution. Through the study of IC 1101, we are not just learning about one of the largest galaxies in the universe. We are gaining insight into the forces that have shaped the universe itself. We are exploring the deep mysteries of galaxy formation, the role of dark matter, the evolution of supermassive black holes, and the interconnectedness of the universe's vast cosmic structures. IC 1101 serves as a beacon for future exploration, guiding astronomers and scientists as they seek to unlock the many secrets of the cosmos. In the grand scheme of things, IC 1101 is just one small piece of the cosmic puzzle. Yet, it represents the culmination of billions of years of cosmic history, a history that is still unfolding as we continue to explore the far reaches of the universe. Its size, age, and unique characteristics make it an invaluable object of study, one that will continue to captivate the imagination of astronomers and the general public alike for many years to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.